The transition from the dense architecture of the coral city to the open plains of the seafloor feels like a release of tension. The jagged walls and shadowed corridors give way to a sprawling expanse of pale sediment, broken shell fragments, and undulating currents. To the naked eye, this boundary looks like the edge of the world, a place where the complexity of life simply runs out of material to build with. The water here is brighter. The sight lines stretch for yards, and the shadows have nowhere to anchor. It is an environment that suggests complete transparency. Fish that swim through the zone adjust their behavior, cruising slightly higher in the water column, trusting their eyes to spot approaching danger from a distance. The underlying assumption of the open flat is that danger must travel to reach you. It must cross the empty space, and in doing so, it must reveal itself. But the seafloor is a masterclass in deception. It relies on the observer's deeply ingrained belief that an empty surface is a safe surface. The ground beneath the drifting currents is not a canvas waiting for a predator to arrive. The ground itself is watching. If you stare long enough at the rippling patterns of light dancing across the grains of sand, the illusion slowly begins to fray. It does not happen all at once. The mind struggles to process what the eyes are transmitting because the geometry is wrong. A patch of sand seems to lift infinitesimally against the rhythm of the current. A faint, almost imperceptible ridge forms a soft, diamond-shaped perimeter that shouldn't exist in the random scatter of the ocean floor. It is only when the focus shifts to two small, raised mounds, eyes swiveling with independent, calculated precision, that the realization sets in. The stingray has not just arrived. It has been there the entire time. This is a masterstroke of biological integration. The stingray does not seek shelter behind an object. It adopts the identity of the substrate. Its body is dusted with the exact mineral composition of the surrounding area, a perfect color match maintained by specialized skin cells and a deliberate, shivering motion that settles a layer of the seafloor over its back. Behind the eyes, small valves known as spiracles open and close with a hypnotic, rhythmic pulse. They draw clean water in from above the sand line, flushing it over the gills located on the creature's underside, ensuring respiration continues without disturbing the delicate camouflage. The rest of the animal is a study in absolute, unbroken stillness. This posture is not rest. It is a state of perpetual, vibrating vigilance. To understand the stingray is to understand a creature built entirely for the boundary between water and earth. Its flattened shape is the result of extreme evolutionary pressure, an adaptation that turned the standard fish blueprint into a glider. The pectoral fins have expanded outward, fusing with the head and body to create wide, muscular wings. This design eliminates drag, allowing the stingray to hover just millimeters above the sand with almost zero energetic cost. But this extreme specialization creates a profound vulnerability. With its eyes positioned squarely on the top of its head, and its mouth relegated to the underside, the stingray exists in a state of sensory division. It watches the sky, but it feeds on the earth. Its daily routine is surprisingly peaceful, betraying the violent reputation it carries. The stingray is a forager, not a pursuer. It glides over flats, using an array of electroreceptors scattered across its snout to detect the faint, electrical hum of buried life. The heartbeat of a hidden crab, the muscle twitch of a clam buried deep in the sediment. When it locates a target, it drops down, pressing its heavy disc against the bottom. The wings undulate rapidly, sending jets of water downward to excavate the sand, trapping the prey beneath its body. Specialized crushing plates in the underslung mouth go to work, grinding through calcified shells to extract the soft tissue within. It is a slow, methodical existence, one focused entirely on the small and the hidden. But the ocean does not allow any creature to forage without consequence. While the stingray focuses on the sand, it becomes a target for anything patrolling the water column above. Large sharks and transient predators view the flat expanse as a hunting ground, and a stingray pressed against the bottom is a substantial meal lacking the speed to outrun a dedicated pursuit. Because its body is flattened, it cannot pivot sharply or accelerate vertically with the explosive force of a torpedo-shaped fish. Its gills, its vital organs, its soft underbelly, all are pinned against the ground, trapped by the very shape that allows it to forage so effectively. When a threat descends from above, the stingray cannot turn to face it. It cannot bare its teeth or posture aggressively. It is biologically tethered to the floor. Evolution answered the spatial dilemma not by altering the stingray's body, but by weaponizing its anatomy in reverse. Trailing behind the wide, graceful disc of its body is a tail that seems completely out of place. It is long, slender, and whip-like, dense with fast-twitch muscle fibers, and anchored near the base of this appendage, or sometimes situated further down its length, is the instrument that gives the animal its name, the barb. In silhouette, it looks like a crude spike, but closer inspection reveals a biological weapon engineered with terrifying sophistication. The barb is a modified dermal denticle, hardened and calcified into a rigid blade. It is not smooth. Its edges are lined with jagged, backward-facing serrations that feel like the teeth of a saw. Running along the underside of this blade are twin longitudinal grooves, and nestled within these grooves is a sheath of glandular tissue that constantly produces a complex, highly stable venom. This is not a hunting tool. The stingray never uses its tail to capture the crabs or mollusks it eats. The barb is reserved exclusively for the moments when camouflage fails, when the shadow passes directly overhead, and when escape is no longer a mathematical possibility. When danger approaches, the stingray does not immediately react. It trusts its invisibility. It waits as the pressure waves of a large predator or the heavy footfall of a wading human ripple through the water. It calculates the proximity through a lateral line system that feels the displacement of water long before physical contact is made. In these suffocating moments, the stingray remains perfectly inert. But if the boundary is crossed, if a jaw attempts to snap down or a weight presses against its buried wings, the transition from passive camouflage to explosive violence occurs in a fraction of a second. The strike of a stingray is a masterclass in kinetic transfer. Powerful muscles at the base of the tail contract, sending a shockwave of energy down the appendage. The tail lashes upward and forward in a blinding arc, snapping over the stingray's own back like a scorpion strike. It moves so fast that it creates a localized disturbance in the water, a blur of motion that the human eye can barely track. The target does not matter, whether it is the snout of a shark or the ankle of a fisherman. The physics remain the same. The serrated blade drives deep into flesh with the force of a driven nail. The initial puncture is brutal, but the true devastation occurs in a fraction of a second that follows. Because the serrations point backward, the barb resists extraction. As the tail naturally recoils, the jagged edges catch and tear the surrounding tissue, turning a clean puncture wound into a ragged, lacerated trench. Simultaneously, the thin sheath covering the venom grooves ruptures under friction of entry, forcing the toxic cocktail directly into the deepest part of the wound. The venom itself is a masterpiece of deterrence. It is not designed to kill. Killing an attacker takes time, and time is a luxury a pinned stingray does not possess. Instead, the venom is composed of proteins and enzymes specifically engineered to overload the nervous system with immediate, localized agony. It triggers severe muscle cramps, intense swelling, and a burning sensation that radiates rapidly from the point of impact, often causing temporary paralysis in the affected limb. The pain is not a byproduct. It is the entire point. It is a biological scream, a violent command to let go. For a predator, the sudden influx of searing pain overrides a predatory drive instantly. A shark that expected an easy meal suddenly finds its jaw throbbing, its senses overwhelmed by agony. The instinct to consume is entirely replaced by the instinct to retreat. For a human, the experience is described as excruciating, a medical emergency that leaves the victim breathless and incapacitated, often complicated by the fact that the brittle barb can snap off during the violent recoil, leaving a jagged, venom-leaching fragment embedded deep within the muscle. The stingray does not wait to observe the results of its defense. It has no interest in victory, only in survival. The moment the tail recoils, the animal utilizes the chaos. With a massive, synchronized downward beat of its wings, it launches itself off the seafloor. The movement kicks up a thick, blinding cloud of sand and sediment, a smoke screen that obscures its trajectory. By the time the water clears, the flat appears completely empty once more. The attacker is left completely alone, nursing a wound that will ache for days, learning a lesson that will alter its behavior for the rest of its life. This is how the stingray shapes the ecosystem without ever behaving aggressively. It does not patrol its territory, it does not bare its teeth, and it does not challenge rivals. It simply alters the psychological map of the reef. Predators that share the environment learn to read the subtle disruptions in the sand. They learn that the open flats are not a free thoroughfare, but a minefield. They begin to swim higher, to approach sandy depressions with hesitation. The presence of the stingray turns the very act of touching the bottom into a calculated risk. It demands respect through the promise of disproportionate consequence. The elegance of this system lies in its absolute restraint. The stingray does not want to strike. It expends significant energy to remain hidden, to breathe without moving, to live entirely in the margins. Every deployment of the barb carries a risk of damage, and regrowing a broken spine requires metabolic investment. The tail is a last resort, a hidden knife kept sheathed until the exact moment the world attempts to crush it. It is a predator of small things that carries a weapon capable of humbling giants. It reminds every creature that wanders out of the dense coral and onto the open sand that emptiness is an illusion. The floor is armed, and it does not forgive a careless step. The shallows of a coral reef exist in a state of permanent optical fracture, where the deep ocean is defined by suffocating pressure and endless blue. The reef margins are defined by chaos. Sunlight does not simply illuminate this space. It shatters against a turbulent surface, sending down kinetic webs of light that constantly shift, expand, and collapse across the seabed. The water here is rarely clear. It is thick with a suspension of life and decay, drifting grains of pulverized limestone, torn strands of algae, and the microscopic haze of plankton. To look down into this shallow transitional zone is to subject the brain to a relentless assault of visual information. There are no clean lines. There is no empty space. Everything is covered in something else. Rock is coated in sponge. Dead coral is wrapped in turf algae. Sand is littered with the shattered architecture of past storms. It is an environment of overwhelming clutter, a place where the eyes are so burdened with detail that they begin to take shortcuts, ignoring the background to focus only on movement. And it is precisely within this cognitive blind spot that the stonefish builds its empire. To call the stonefish camouflage is a fundamental misunderstanding of what camouflage usually means. Most animals attempt to hide by matching a color or mimicking a specific shape, like a leaf or a stick. They try to disappear by being inconspicuous. The stonefish does the exact opposite. It disappears through excess. It recognizes, on a deep evolutionary level, that the reef floor is a mess of irregular textures, and it adopts that mess as its own physical form. Its body is devoid of the sleek, hydrodynamic lines that define almost every other fish in the ocean. There are no smooth scales, no aerodynamic curves, no tapering fins designed to cut through water. Instead, the stonefish is an aggregate of biological lumps, craters, and fleshy extensions that perfectly mimic the eroded, algae-choked rubble of a dead reef. Its skin is a canvas of decay. It is mottled in dull, mineral hues of rusted brown, olive green, and ashen gray. But the deception goes far beyond pigmentation. The skin itself is highly textured, pitted and ridged, and it acts as a living substrate. The stonefish secretes a specialized mucus that actively encourages the growth of marine algae and tiny, sedentary invertebrates directly on its body. Over time, the boundary between the animal and the environment ceases to exist. It literally wears a reef. When seen from above, the perspective of almost every predator or wandering grazer, the outline of the fish completely dissolves. The symmetry that usually triggers recognition in a predator's brain is entirely absent. It has removed itself from the visual vocabulary of the ocean. It is no longer a fish. It is a mistake in the viewer's perception. This extreme commitment to invisibility dictates everything about how the stonefish lives. In the warm, oxygen-depleted waters of the extreme shallows, movement carries a massive metabolic penalty. Energy is a precious currency, and the stonefish refuses to spend it. It does not patrol a territory. It does not actively hunt or pursue prey. It embraces a life of profound, uncompromising stillness. A stonefish can remain locked in the exact same position for days, entirely motionless, its respiration slowed to an almost imperceptible rhythm. The gills barely flare. The eyes, perfectly matching the surrounding rock, do not dart or track. It relies completely on the assumption that it will not be seen, and that eventually, the ocean will deliver a mistake directly to its mouth. When that mistake arrives, The transition from inertia to violence is so fast it seems to violate the laws of physics. A small fish, perhaps a damselfish or a wandering crustacean, drifts into the airspace just above the seemingly inert rock. The prey is completely relaxed, scanning the water column for threats, ignoring the seabed because the seabed is not supposed to have a jaw. The stonefish does not tense. It does not wind up or adjust its posture. It waits until the target crosses an invisible, microscopic threshold of proximity. Then the jaw drops. It is not a bite. Biting requires lunging, and lunging requires the movement of the entire body, which would ruin the disguise. Instead, the stonefish utilizes extreme suction feeding. By rapidly expanding the bones of its skull and dropping its massive lower jaw in a fraction of a millisecond, it creates a sudden, catastrophic drop in pressure within its oral cavity. The water directly in front of the fish's face instantly collapses into this newly formed void, dragging the prey along with it. The acceleration is so intense that the victim has no time to register fear, let alone trigger the neuromuscular signals required to flee. In less time than it takes a human eye to blink, the space above the rock is simply empty. The jaws snap shut. The displaced sand slowly drifts back down to the seabed. There is no struggle, no frantic thrashing, no cloud of blood to attract scavengers. Predation has occurred without a single ripple of spectacle. But it is not this invisible, vacuum-like hunting method that has made the stonefish a creature of global infamy. Its ability to delete prey from the water column is merely how it sustains itself. How it defends itself is another matter entirely. The shallows are dangerous not just for small fish, but for the stonefish as well. This is a collision zone of the ocean, the place where heavy, clumsy animals interact with the seabed. See turtles drag themselves across the rubble. Sharks patrol the extreme margins, their bellies scraping the sand. And humans, wading, walking, stepping off boats, use the shallows as a thoroughfare, their eyes locked on the horizon, their heavy feet coming down blindly on the hidden architecture of the reef. The stonefish cannot afford to be crushed, but because it has sacrificed all its speed and agility for the sake of camouflage, it cannot swim away when a shadow falls over it. Fleeing would not only expose it to faster predators, but it would require an expenditure of energy it is not designed to support. So, the stonefish simply refuses to move. It holds its ground, and it deploys the most sophisticated, passive defense mechanism ever engineered by marine evolution. Running along the ridge of its back, concealed entirely by the fleshy, algae-covered illusion of its skin, are 13 dorsal spines. They do not look like weapons. They are thick, rigid, and appear as structural as a jagged piece of dead coral. They do not wave or flare aggressively like the warnings of a lionfish. They simply point upward, breaking the horizontal plane of the animal's back just enough to intersect with whatever is coming down from above. These spines are the delivery mechanism for a venom system that is horrifying in its mechanical simplicity. The stonefish does not possess the ability to actively inject its venom. It has no muscles wrapped around its venom glands to forcefully squeeze the toxin into a victim. It does not need them. The system is designed to use the attacker's own weight and momentum against it. At the base of each of the 13 spines lies a pair of large, highly pressurized venom glands. The spines themselves are grooved, acting like hypodermic needles. When a descending foot, fin, or jaw presses down on the back of the stonefish, the pressure forces the fleshy sheath surrounding the spine downward. This mechanical compression squeezes the venom glands at the base. As the sharp, rigid spine punctures the flesh of the intruder, the venom is driven forcefully up the grooves and injected deep into the wound. The stonefish does not make a decision to sting. The act of being stepped on pulls the trigger automatically. It is a system built entirely on the inevitability of physics. The venom that enters the victim is a complex, devastating cocktail of proteins, primarily a myotoxin known as stonefistoxin. It is engineered not to kill, but to inflict a level of pain so absolute and overwhelming that it instantly shatters the attacker's will to continue. In the context of the animal kingdom, pain is a teaching tool. The stonefish venom delivers a masterclass. Upon injection, the proteins begin immediately attacking the cellular structures surrounding the wound. The venom acts as a potent vasodilator, causing blood vessels to expand rapidly and dangerously, dropping the victim's blood pressure while simultaneously inducing localized necrosis, the death of tissue. But the true horror is neurological. The venom forces nerve endings to fire continuously, transmitting a signal of pure, unadulterated agony to the brain. For a marine predator that attempts to bite down on a stonefish, the sensation is immediate and catastrophic. The jaw locks in agony, the mouth opens, and the stonefish is released. The predator thrashes away, its feeding instinct entirely erased, replaced by a desperate, blinding panic. It will never, under any circumstances, attempt to eat anything that looks like that patch of rock ever again. For a human who steps blindly onto a reef flat, the experience is life-altering. The pain is frequently described as the most excruciating sensation a human body can endure, far surpassing the agony of childbirth, kidney stones, or severe burns. It does not throb. It radiates, crawling up the affected limb like a fire beneath the skin. The physiological shock of the pain can be so severe that it induces delirium, vomiting, and in extreme cases, respiratory failure and cardiac arrest. The venom attacks the cardiovascular system, turning a simple misstep in ankle-deep water into a desperate fight for survival. And through all of this, through the screaming, the thrashing, the violent retreat of the attacker, the stonefish does not move. It does not gloat. It does not flee in the aftermath. It simply remains where it was, its spines automatically resetting as the pressure is removed, its camouflage entirely uncompromised. The environment absorbs the violence, and the stonefish fades back into the visual noise of the reef, indistinguishable from the stones that surround it. This extreme localized defense turns the stonefish into a static regulator of the entire ecosystem. It does not roam the reef, imposing its will upon the populations of fish and invertebrates. Instead, it alters the way the reef is navigated. The presence of stonefish creates invisible, highly punitive zones across the shallows. Grazing animals, constantly probing the bottom for algae, learn to read the microscopic variations in the rubble, avoiding spaces that seem slightly too elevated, slightly too textured. Larger predators learn that the seafloor is not a safe place to rest their bellies. The stonefish enforces a strict, unspoken law upon the reef. Watch where you put your weight. It is a creature that has completely opted out of the biological arms race of speed, agility, and aggressive conquest. It does not chase its food, and it does not run from its enemies. It has found absolute perfection in the art of doing nothing. It relies entirely on the flaws and perception of others, punishing their blindness with a ruthless, automatic chemistry. To look at the shallows and see only sand and stone is to fall for the oldest trick in the ocean. The stillness is a lie. The rock is breathing. And if you force it to prove that it is alive, it will make sure you never forget the answer. Just beyond the pristine, sunlit architecture of the coral gardens lies a boundary that few observers ever linger on. It is the place where structure inevitably surrenders to gravity and decay. The sheer vertical drop-offs and intricately branching coral heads give way to a sloping basin of shattered limestone, empty shells, and shifting sand. This is the reef's collection plate. Every ecosystem, no matter how vibrant or perfectly balanced, generates a continuous rain of ruin. Currents sweep across the upper terraces, picking up the aftermath of the day's violence. The torn fin of a hunted fish, the discarded exoskeleton of a molten crustacean, the half-eaten remains of a predator's midnight kill. All of it slowly sinks, guided by the hydrodynamics of the ocean, until it settles into the shadowed depressions of the rubble fields. It is a graveyard of fragments, a zone defined entirely by what has been left behind. But in the ocean, a graveyard is never a place of rest. It is a place of absolute, unapologetic opportunism. And the moment organic matter touches this broken ground, the cleanup crew arrives. They emerge from a porous rock and the dark gaps between the rubble like an invading army of living machinery. The crabs, they do not approach with the sleek, hydrodynamic grace of a cruising shark, nor do they possess the mesmerizing, fluid intelligence of an octopus. A crab's movement is rigid, mechanical, and governed by the geometry of its joints. They scuttle sideways, their armored legs picking precisely through the debris, antennae flicking erratically to taste the chemical signatures drifting in the water. They are the ultimate pragmatists of the marine world. They do not care about the glory of the hunt. They care only about calories. And they are built to extract them from the wreckage that others ignore. When a crab locates a food source, a decaying fish carcass lodged between two stones, for instance, There is no subtlety to its process. It does not nip or graze. It dismantles. The oversized claws, driven by dense bundles of muscle encased in hard chitin, act as both crowbars and shears. They pry apart rib cages, tear through tough ligaments, and crush remaining bone to get to the marrow and muscle left within. As more crabs arrive, drawn by the undeniable scent of biological breakdown, the scene descends into a ruthless, clattering frenzy. It is a brutal economy of scale. They fight one another for position, armored shells clicking and grinding as they rip the prize to shreds. They feed openly, trusting their thick exoskeletons to protect them from the occasional passing predator. In this moment, they seem perfectly adapted, thriving in an environment that rewards speed, armor, and a lack of discrimination. However, this frantic consumption masks an insidious, invisible reality. The reef is not a safe place, and the things that die within it do not always surrender their weapons simply because their hearts have stopped beating. The reef is heavily populated by creatures that rely on extreme chemical warfare for their survival. Pufferfish brimming with tetrodotoxin, sea slugs concentrating toxic sponges into their own flesh, and venomous predators carrying concentrated neurotoxins. When one of these animals dies, whether from disease, old age, or a predator that killed it but recognized the danger too late and abandoned the carcass, its body drifts down into the scavenging zones. To the crabs, a toxic carcass looks exactly the same as a harmless one. The sensory world of crab is highly attuned to the scent of amino acids and decay, but is entirely blind to the molecular presence of defensive poisons. A dead pufferfish does not broadcast a warning. Once the animal stops moving, the visual and behavioral cues that signify danger are gone, but the chemistry remains. Toxins are exceptionally resilient compounds. They are designed to withstand the harsh environments of digestive tracts and bloodstreams, which means they do not immediately break down when an animal dies. The venom stored in the spine, the poison woven into the liver of a fish, the toxic mucus coating in nudibranch, all of it persists in the dead tissue waiting. When the crabs tear into these toxic carcasses, they are not just consuming calories. They are ingesting the physiological history of the animal. They are eating its defenses. In any other context, this would be an immediate and fatal mistake. A mammal or a typical fish consuming a concentrated dose of marine neurotoxins would suffer catastrophic failure within minutes, paralysis, respiratory collapse, and death. But the scavenging crabs possess a physiological loophole. Through millions of years of living as the ocean's garbage disposals, they have evolved incredibly robust metabolisms and highly buffered internal chemistry. They are not entirely immune to all toxins, but they have an astonishing tolerance. They can consume highly toxic flesh, process the nutrients they need, and sequester the harmful compounds without dying. The crabs survive not by fighting the poison, but by carrying it. Furthermore, their feeding behavior acts as a biological dilution mechanism. A crab does not sit and consume an entire toxic carcass alone. The frenzy of a scavenging zone ensures that a single dead pufferfish is torn apart and consumed by dozens, perhaps hundreds, of individual crabs. The toxic load is divided, spread across a massive population. No single crab absorbs a lethal dose, but the entire population becomes chemically charged. They act as microscopic sponges, soaking up the ambient lethality of the reef and locking it inside their own tissues. This is where the dynamic of the reef takes a terrifying, invisible turn. The danger has not been eliminated by the death of the toxic animal. It has simply changed vehicles. The crab, an animal with no venom glands, no stingers, and no ability to synthesize poison, has inadvertently become a biological weapon. Eventually, the feeding frenzy ends. The crabs scatter, their bellies full, their bodies humming with stolen chemistry, and they blend back into the wider ecosystem. And the wider ecosystem loves to eat crabs. An octopus extending a silent arm into a crevice, a moray eel snapping its jaws in the dark, a heavy-bodied grouper inhaling a careless target. These predators rely on crabs as a staple of their diet. The armor of a crab is easily bypassed by the specialized tools of these hunters. The predator crushes its shell, digests the meat, and assumes the interaction is over. It believes it has won. But digestion is not a neutral process. The gut is the ultimate gateway into the bloodstream. As the predator breaks down the crab's tissues, it unwittingly releases the sequestered toxins right back into its own system. The poisoning is rarely dramatic. The predator does not instantly seize and die on the ocean floor. The dose delivered by a single crab is usually sublethal, a microscopic fraction of the original dead animal's payload. But marine neurotoxins are highly specific, targeting the fundamental communication networks of the body, the sodium channels, the synaptic gaps, the firing of muscle fibers. As the predator digests the crab, these compounds begin to interfere with its nervous system. The effects are insidious. A moray eel might find its jaws closing a fraction of a second slower than usual. An octopus might experience a slight tremor in its arms, a momentary lapse in the fluid coordination required to pin a struggling fish. A grouper might feel a subtle, lingering fatigue that causes it to abandon a hunt it would normally finish. In a human, these symptoms will be recognized as sickness. In the ocean, where the margin between eating and starving, between escaping and being eaten, is measured in milliseconds, these symptoms are a death sentence. A predator operating at 95% efficiency is a predator that is slowly dying. It misses strikes. It expends more energy for fewer calories. It becomes sluggish, making it vulnerable to larger predators that it would normally evade with ease. The toxin does not kill the apex predator directly. It simply tilts a mathematical probability of survival against it. If the predator relies heavily on the scavenging zones, hunting crab after crab, the effect compounds. The bioaccumulation of toxins builds up in the predator's liver and muscle tissues. The weakness deepens. The predator begins to waste away, fundamentally compromised from the inside out, never understanding that it is being killed by the lingering ghost of an animal it never even encountered. This creates a terrifying reality within the architecture of the coral reef. There are zones of the ocean floor that become completely saturated with risk, yet they contain no obvious threats. There are no sharks circling, no stingrays buried in the sand, no stonefish waiting in the rubble. It is just a field of broken coral and scavenging crabs. Yet, to hunt heavily in these zones is to invite a slow, invisible collapse. The venom has been divorced from the animal that created it. It flows upward to the food web, defying the traditional hierarchy of power. The apex predator is brought down not by a rival, but by the garbage collectors. The crabs themselves remain entirely indifferent to this consequence. They are unaffected by the chaos they distribute. They continue their mechanical patrol of the rubble, waiting for the next carcass to fall. They represent a fundamental truth of the ecosystem that is easily overlooked by those who only study the dramatic clashes of teeth and claws. Power is not always about who is the strongest in the moment of impact. Sometimes, the most devastating weapon on the reef is memory. The ecosystem remembers the poison long after the creator is dead. It passes it from the dead flesh to the scavenger to the predator, a silent chain of consequence carried entirely within the gut. The crabs do not fight the predators that hunt them. They simply allow themselves to be eaten, knowing, on some invisible biological level, that their armor is not their shell. Their true armor is a delayed vengeance of the things they have consumed. The predator wins a battle for the meal, but it loses a war for its nervous system. On the reef, you are not just what you eat. You are what your prey ate yesterday. Where the coral architecture builds itself into rigid, calcified towers, the ocean eventually demands a contrast. Among the jagged ledges and the unyielding plates of limestone, the reef occasionally softens. Here, rooted in the hollows and crevices of the stone, blooms something that looks entirely out of place in a world governed by armor and teeth. It sways with the rhythm of the surge, a collection of fleshy, translucent ribbons catching the fractured light. It is brightly colored, hypnotic, and completely devoid of the sharp edges that define survival in the shallows. To a human eye, it is the ocean's imitation of a flower. To the inhabitants of the reef, it appears to be a sanctuary, a patch of gentle motion in a landscape of unforgiving rock. But the sea anemone is not a plant, and it is certainly not a sanctuary. It is one of the most concentrated, highly engineered minefields on the planet. To understand the anemone, you must discard the assumption that a predator needs to be mobile. In the logic of the ocean, we associate lethality with forward momentum. The burst of a shark, the strike of an eel, the suction of a grouper. The anemone possesses none of these. It lacks a skeletal structure, it has no brain, and once it finds a suitable crevice, it essentially glues its basal disc to the rock and stops moving. It commits entirely to a philosophy of absolute, unyielding stillness. It does not hunt. It does not chase. It does not hide. It simply occupies space and waits for the world to make a mistake. The deception lies in the tentacles. There are dozens, sometimes hundreds of them, drifting lazily in the current. They look like sensory organs or soft fronds meant to filter the water. They are neither. They are the delivery system for a weaponized biology so microscopic and so fast that it defies standard muscular physics. Every square millimeter of an anemone's tentacle is densely packed with specialized cells called cnidocytes. And within each of these cells sits a capsule known as a nematocyst. You cannot see them, but they are there by the millions. A nematocyst is not a venom gland that requires a bite to deliver its payload. It is a self-contained, mechanically loaded, pressurized harpoon. Inside the microscopic capsule, a hollow, barbed thread is tightly coiled, suspended in a cocktail of neurotoxins, and bathed in a solution that creates immense internal osmotic pressure. Protruding from the top of the cell is a tiny, hair-like trigger called a cnidocyl. This is the tripwire. The anemone does not have a central nervous system to make a conscious decision to attack. It does not look at a passing fish and decide to fire. It has completely outsourced the act of killing to autonomous cellular mechanics. When a fish swims too close, assuming the soft fronds are safe to brush against, the interaction is doomed before the animal even registers contact. The trigger requires two distinct inputs to prevent misfiring: physical pressure from the touch and the chemical signature of biological tissue. A piece of drifting seaweed brushing the tentacle does nothing, but the mucus-coated scales of a living fish satisfy both conditions instantly. The firing of a nematocyst is one of the most explosive cellular events known to science. It happens in less than 3 milliseconds. When the trigger is tripped, the lid of the capsule flies open. The immense internal pressure is suddenly released, and the coiled, barbed thread violently unspools, turning itself inside out as it erupts from the cell. It accelerates at an unimaginable force, crossing the microscopic gap and punching directly through the scales, skin, and soft tissue of the victim. And it is never just one, because the tentacles are draped across the water column. Brushing against them trips thousands of these cellular tripwires simultaneously. The fish is hit by a microscopic firing squad. The barbs lock into the flesh, tethering the prey to the tentacle, while the hollow threads act as hypodermic needles, pumping a devastating complex of neurotoxins and tissue-destroying enzymes directly into the bloodstream. The venom is designed for immediate, catastrophic disruption. It attacks the nervous system, severing the communication between the prey's brain and its muscles. The fish seizes. Its body arcs in violent, uncontrollable spasms. The fins lock, the gills flare, and within seconds, the frantic struggle collapses into total paralysis. The contrast between the speed of the strike and what follows is chilling. The anemone fired its weapons in a fraction of a millisecond, but it feeds with glacial patience. The prey, now immobilized but entirely alive, remains tethered to the sticky, barbed surface of the tentacles. Slowly, almost imperceptibly, the arms begin to curl inward. They do not snap shut. They bend with a gentle, methodical contraction, folding the paralyzed victim toward the center of the anemone's body, where a simple, gaping mouth awaits. The fish is swallowed whole, dragged alive into the gastric cavity where digestive enzymes will slowly dissolve it. Hours later, the anemone will simply spit out the bones and scales. The tentacles will unfurl back into the current, and the minefield will be completely reset. This mechanism allows a creature with no brain and no bones to exert a massive psychological and physical footprint on the reef. The anemone becomes a fixed point of absolute consequence. Predators and grazers alike quickly learn the geography of the reef, mapping out the locations of these swaying fortresses. They alter their swimming paths, maintaining a wide, respectful perimeter. The anemone does not need to patrol its territory because its reputation does the patrolling for it. It dictates the flow of traffic in its immediate vicinity, creating invisible borders that the rest of the ecosystem dare not cross. Yet, as you watch this lethal perimeter, a glaring contradiction reveals itself. Darting through the water, colored in bright, unmistakable bands of orange and white. A small fish swims directly into the heart of the weapon. The clownfish does not just touch the tentacles. It bathes in them. It buries its face in the cnidocytes, wiggles its body deep into the center of the anemone, and rests there completely unharmed. The harpoons do not fire. The venom is not injected. The trap remains dormant. To the uninitiated, this looks like immunity, a case of a fish evolving to survive the poison. But the reality is far more elegant and far more deceptive. The clownfish does not fight the venom because the clownfish ensures it is never fired upon. It survives not through strength, but through a masterful act of chemical espionage. When a young clownfish first seeks out an anemone, it knows it cannot simply swim inside. If it did, it would be paralyzed and eaten just like any other fish. Instead, it begins a slow, agonizingly careful dance of acclimation. It hovers at the edge of the tentacles, letting a single fin brush against the tips, then rapidly retreating. It repeats this process over and over, enduring minor, non-lethal stings. What it is doing is deliberately smearing itself with the anemone's own bodily mucus. The nematocyst triggers, as mechanical as they are, rely on chemical recognition to confirm that the object touching them is foreign prey. The anemone's tentacles are constantly rubbing against one another in the current to prevent the anemone from stinging itself to death. Its mucus contains a specific chemical signature that tells its own cells not to fire. The clownfish steals the signature by slowly coating its entire body in the anemone's mucus. It effectively dons an invisibility cloak. To the microscopic tripwires of the anemone, the clownfish no longer registers as a fish. It registers as just another tentacle. The clownfish has hacked the biological programming of the reef's most sophisticated weapon. Once this chemical handshake is complete, one of the most formidable alliances in the ocean is formed. The clownfish gains an impenetrable fortress. In the open water, a clownfish is a terrible swimmer, slow, highly visible, and an easy meal for almost any predator. But wrapped in the arms of the anemone, it is invincible. No predator, regardless of its size or speed, is willing to risk a face full of neurotoxic harpoons to catch a single clownfish. But the relationship is not a one-way exploitation. The anemone is a static creature. It cannot defend itself against specialized predators that have evolved to eat its tentacles, like certain butterfly fish or sea turtles. This is where the clownfish pays its rent. Emboldened by the absolute security of its home, the tiny clownfish becomes an aggressively violent perimeter guard. If a butterfly fish approaches to nip at the anemone, the clownfish launches itself in the tentacles like a missile, biting and chasing the intruder away before darting back to safety. It acts as the anemone's mobile strike force. Furthermore, the clownfish is a meticulous caretaker. It aggressively wiggles through the tentacles, increasing water flow and oxygenation to the anemone's tissues. It meticulously picks away dead debris and parasites. And because the clownfish lives its entire life within inches of the host, its biological waste acts as a highly concentrated, localized fertilizer, feeding the symbiotic algae that live within the anemone's flesh. They are a perfect, self-sustaining loop of violence and nourishment. The anemone provides a heavy artillery. The clownfish provides a maintenance and the early warning system. This dynamic completely subverts our understanding of power in the wild. We expect power to look like muscle. We expect it to be loud, fast, and imposing. But the sea anemone proves that the ultimate form of dominance is not needing to move at all. It sits in the open, radiating soft, beautiful colors, looking for all the world like a fragile piece of underwater foliage. It invites the eye, it invites the current, and it invites contact. It has taken the fundamental weakness of being rooted to the floor and turned it into an inescapable advantage. It does not exert energy searching for the ocean's mistakes. It simply builds a machine that punishes them automatically. As the currents push and pull against the reef, the anemone continues its gentle, hypnotic sway. The clownfish weaves through the lethal threads, a bright spark of life inside a cage of hidden death. The reef around them remains tense, a constant negotiation of boundaries and threats. But within the radius of those soft tentacles, the negotiation is over. There is no chase, no struggle, and no second chance. There is only the stillness, the touch, and the immediate, microscopic violence of consequence. Where the towering, vertical architecture of the upper reef begins to surrender to the deep, The topography undergoes a fundamental shift. The sheer walls and crowded coral canopies flatten out, giving way to a gentle, sweeping incline. This is a lower terrace, a mosaic landscape of isolated coral heads, rolling sand channels, and low, deeply undercut ledges. The frenetic energy of the sunlit shallows does not reach down here. The light is heavier, filtered into cool bands of blue and green that stretch the shadows across the limestone. Water moves differently in this space. It does not crash or surge. It pulls with a steady, unrelenting draw. The animals that inhabit this transitional zone do not navigate by frantic sprinting. Survival here is a matter of buoyancy, positioning, and an intimate understanding of the spaces between the stones. In this environment, motion is constant, but it is rarely fast. Small fish drift in loose aggregations, suspended a few feet above the substrate, adjusting their altitude with microscopic flicks of their fins. They are always aware of the seabed beneath them, but their attention is a generalized anxiety, scanning the open water for familiar silhouettes of cruising sharks or darting jacks. They are looking for predators that move like predators, creatures of speed built to close the distance. They are anticipating a chase. But the lower reef harbors a predator that entirely rejects the premise of the chase. From the dense, impenetrable shadow beneath a limestone overhang, a shape begins to detach itself. It does not dart into the light. It emerges with a slow, deliberate certainty, displacing the water with the sheer density of its mass. This is the grouper. To look at the grouper is to look at a creature that seems to defy the aerodynamic rules of the ocean. It is not sleek. It possesses none of the torpedo-like streamlining of a tuna or the muscular curvature of a reef shark. Its body is heavy, laterally compressed, and anchored by a massively disproportionate skull. The jaw is cavernous, the lips thick and downturned, giving the animal an expression of perpetual, brooding indifference. Its fins are broad and paddle-like, designed for fine-tuned stabilization rather than sustained forward propulsion. Everything about its physical form suggests lethargy. It hangs just inches above the sand, its oversized pectoral fins fanning with slow, hypnotic rhythm, keeping its immense bulk perfectly hovering in place. To a small fish, the grouper simply does not register as an immediate threat. It looks too heavy, too sluggish to mount a successful pursuit, and the small fish is entirely correct. The grouper cannot outswim the darting silver flashes of the reef's smaller inhabitants. If a chase were to occur, the grouper would lose almost immediately, its heavy body quickly burning through its oxygen reserves. But the grouper has no intention of chasing anything. It has evolved to solve the problem of speed, not by becoming faster, but by rendering the concept of speed completely irrelevant. The grouper is an architect of proximity. It settles near a natural bottleneck, a narrow channel between two coral heads, or the edge of a drop-off where currents funnel passing traffic. It adopts a posture of profound stillness, its mottled skin blending perfectly with the shadowed rock behind it. Its eyes, resting high on that massive skull, operate with independent articulation. One eye rolls downward to monitor a crab shifting in the sand. The other tracks upward, locking onto a small school of fish drifting with the current. The grouper does not evaluate its prey based on trajectory or velocity. It is performing a ruthless, real-time calculus of distance. In the complex geometry of the reef, prey animals bet their lives on a single, highly evolved reflex, the startle response. The moment a threat is perceived, the specialized neural pathway triggers a massive, instantaneous contraction of fast-twitch muscle fibers. The fish bends itself into a C shape and violently snaps back, launching itself out of the danger zone in a fraction of a second. This reflex is faster than human thought. It has saved billions of lives over millions of years. It assumes that if the fish can simply react, it can put enough space between itself and the predator's jaws to survive. The grouper's entire hunting strategy is designed to mathematically eliminate that fraction of a second. A small fish separates from its school, drifting downward toward the sand to inspect a tiny crustacean. It is entirely focused on the floor, relying on its peripheral vision to warn it of an incoming rush. The grouper does not rush. It merely pivots. With a millimeter-precise adjustment of its pectoral fins, it aligns the massive cavern of its head so that it points directly at the descending fish. It waits. It allows the prey to close the distance on its own, drifting inch by ignorant inch into the invisible kill zone. The threshold is crossed. The prey is now mere inches from the grouper's face. What happens next is not a bite. Biting is a mechanical action that involves projecting the jaw forward to clamp down on a physical object. Biting gives the prey a physical surface to struggle against. The grouper does not bite the fish. It inhales the space the fish is occupying. In an explosion of highly synchronized biomechanics, the grouper skull fundamentally rearranges itself. Powerful muscles pull the hyoid apparatus, the bony structure at the base of the throat, violently downward. Simultaneously, the gill covers flare outward and the massive jaw drops open. This entire sequence occurs in less than 0.03 of a second by suddenly increasing the internal volume of its mouth and throat by over 40%. The grouper creates a localized, catastrophic drop in pressure. The ocean is instantly forced to fill that void. A powerful, inescapable vacuum forms directly in front of the grouper's face. The water does not simply flow inward, it implodes. It rushes into the open mouth with the force of a submerged hurricane. The small fish never receive the chemical or visual cue to trigger its startle reflex. There is no predator rushing toward it to flee from. The environment itself suddenly betrays it. The water the fish is breathing, the water it uses to suspend itself, the water it relies on to swim, all of it is violently ripped away, dragged backward into the cavern of the grouper's mouth. A cloud of sand and pulverized shell erupts from the seabed, spiraling into the vortex. The prey is sucked inward so violently that its orientation is instantly destroyed. It is pinned against the immense rush of water, folded into the darkness before the electrical signal to flee can even reach its tail. The jaws snap shut with the sound of a heavy door slamming underwater. The physics of the ocean immediately stabilize. The vacuum collapses. Inside the closed mouth, the dynamic changes instantly. The massive volume of water that was just inhaled must go somewhere, or the grouper would choke. The gill covers open wide, and the water is rapidly expelled backward out of the body. But the prey does not flow out with it. Lining the inside of the grouper's mouth and throat are hundreds of tiny, needle-sharp teeth. But unlike the tearing teeth of a shark, these teeth point backward, angling sharply toward the esophagus. They act as a one-way biological ratchet. The rushing water pushes the prey deeper into the throat, and the backward-facing teeth ensure that every struggle, every frantic thrash, only drives a victim further down. Deep within the throat, a second set of jaws, the pharyngeal teeth, grip the disoriented prey and pull it directly into the stomach. There is no tearing of flesh. There is no cloud of blood to draw the attention of scavengers. The fish is swallowed completely whole, vanishing from the ecosystem in a single, uninterrupted motion. Outside, the cloud of disturbed sand slowly drifts back down to the seabed. The grouper's chest heaves once, deeply, as it settles back onto its pectoral fins. It resumes its hovering posture, its eyes rotating back to scan the current. The reef returns to its baseline rhythm. If an observer were to blink at the exact moment of the strike, they would simply assume the small fish had wandered behind a rock. Predation has occurred, but it has left no aesthetic signature of violence. It is an erasure. This hunting method, known as extreme suction feeding, is a biological masterpiece, but it comes with profound constraints. The muscular effort required to generate such a massive pressure differential in a fraction of a second is energetically exhausting. The grouper cannot perform this action continuously. It cannot afford to miss. Every strike must be calculated with absolute certainty, which is why the grouper is the embodiment of patience. It will hover in the shadows for hours, ignoring hundreds of potential meals that are just slightly out of range, just slightly off angle, waiting for the one foolish organism that drifts past the invisible point of no return. This requirement for proximity also drives one of the most remarkable behavioral phenomena on the entire reef. The grouper is a solitary, fiercely territorial creature, but it possesses an intelligence that recognizes the limitations of its own biology. It knows that its massive body cannot penetrate the deep, narrow crevices where smaller fish hide when they are frightened. But the moray eel can. When prey disappears into the impenetrable architecture of the coral, a grouper will sometimes seek out the den of a large moray eel. The grouper will hover near the entrance and perform a specific, rapid shaking of its head, a cross-species invitation to hunt. The eel, recognizing the signal, slithers out its cave and joins the grouper. The two predators navigate the reef together, a terrifying alliance of completely different mechanical functions. The eel is a creature of penetration. It pours its serpentine body through the winding, microscopic tunnels of the limestone, flushing hidden fish from their deepest sanctuaries. The fish, terrified by the jaws of the eel invading their safe room, panic and bolt for the exit, bursting out into the open water. And waiting precisely at the exit, perfectly aligned and hovering in the shadows, is the cavernous mouth of the grouper. The prey flees a predator that relies on tight spaces, only to immediately surrender its life to a predator that deletes space entirely. The eel takes the fish it catches inside the rock. The grouper takes the fish that flee into the open. It is a syndicate of survival, an understanding between two fundamentally different killers that the reef provides nowhere to hide. Through this quiet, implosive violence, the grouper shapes the behavior of the entire lower terrace. It does not need to patrol every inch of its territory to control it. Its mere presence at the intersections of the reef forces the ecosystem to adapt. Fish learn the sight lines. They learn to avoid the dark overhangs and the blind corners. They understand, on an instinctual level, that to venture too close to the shadow is to risk being removed from a world. The grouper does not dominate through endurance, nor does it terrify through spectacle of a bloody chase. It represents a much deeper, more philosophical dread. Within the mechanics of nature, it proves that a creature does not need to be faster than its prey to kill it. It proves that survival is not always a matter of fighting or fleeing. Sometimes, the ocean does not afford you the luxury of a reaction. Sometimes, the space you occupy is simply taken from you. The grouper wins because it understands the ultimate truth of the reef. You cannot outswim a vacuum, and you cannot run from a moment that has already passed. The descent from the brightly lit, wave-battered crest of the reef into the mid-depth zones marks a transition from open expanse to structured chaos. Here, the ocean floor rises up in frozen explosions of calcium carbonate. Coral heads branch outward like petrified forests, creating a three-dimensional labyrinth of interlocking archways, narrow corridors, and sudden dead ends. Light filters down through this canopy in fragmented, shifting bands, casting long, deceptive shadows that hide as much as they reveal. This is not a place for the swift. In a maze where every surface is coated in stinging hydroids or abrasive rock, speed is a liability. For the small fish that navigate this vertical city, survival is a matter of darting from cover to cover, making split-second calculations about geometry and clearance. The primary rule of the mid-reef is simple. If you move fast, you must know exactly where you're going. And floating gracefully in the center of this frantic, calculated motion is a creature that seems to have forgotten the rules of the ocean entirely. The lionfish does not look like a predator. In a world where hunters are stripped down to their most hydrodynamically efficient forms, sleek, muscular, and devoid of excess, the lionfish is an exercise in absolute flamboyance. It hovers in the water column with a casual, almost arrogant buoyancy. Its body is draped in elongated, feathery fins that trail outward in sweeping arcs, drifting lazily with the current. It is painted in striking, high-contrast vertical stripes of deep maroon, burnt orange, and pale white, an aesthetic that mimics the delicate fronds of feather duster worm or the swaying arms of a soft coral. It does not swim so much as it suspends itself, moving with microscopic, fluttering adjustments of its translucent pectoral fins. To the panicked, hyper-alert inhabitants of the reef, this hovering apparition does not register as a threat. It looks like an ornament. It appears slow, cumbersome, and entirely ill-equipped to mount a pursuit. And the prey is right. The lionfish cannot outrun anything on this reef. Its laterally compressed body and trailing drapery of fins make sustained acceleration impossible. If it tried to chase a damselfish through the twisting corridors of the coral, it would fail miserably, exhausting itself in seconds. But the lionfish knows something that the darting silver flashes around it do not. In a labyrinth, chasing your prey is a fool's errand. It is far more efficient to let the labyrinth do the work. Before the lionfish can hunt, it must ensure that it is not hunted. A slow, highly visible fish hovering in the open corridors of the reef should be an immediate target for larger predators, snappers, sharks, or roaming groupers. But the lionfish occupies its space with absolute impunity. The secret to its arrogance lies in the very fins that make it look so delicate. Rising rigidly from its back and extending from its pelvic and anal regions are 18 needle-sharp spines. Unlike the flowing, decorative pectoral fins, these dorsal spines are structurally reinforced and heavily armed. Each one is sheathed in glandular tissue that produces a highly potent, defensive venom. This is not the offensive, paralyzing venom of the sea snake, nor is it the trapdoor death of the stonefish. The lionfish's venom is purely a deterrent, a chemical command broadcast to the entire ecosystem to keep its distance. When a larger predator attempts to take a bite out of this slow-moving target, the rigid spines puncture the attacker's mouth, delivering a localized, searing agony. The venom induces intense inflammation, muscle necrosis, and profound, lingering pain that completely overwrites the predator's desire to eat. The predator spits the lionfish out and flees, its neurological pathways forever associating those maroon and white stripes with immediate regret. Over evolutionary time, this defensive mechanism has granted the lionfish something incredibly rare in the wild: a psychological buffer zone. The predators of its native reefs have learned to recognize its silhouette. They steer clear, giving the lionfish a wide berth. This invisible bubble of clearance is the foundation of its entire hunting strategy. Protected from harassment, the lionfish is free to deploy a method of predation that requires the ultimate luxury: time. The hunt begins not with a burst of speed, but with a slow, deliberate drift. The lionfish targets the small, nervous fish that cling to the vertical walls of the coral heads. These prey fish are hardwired to react to sudden movement. If a predator lunges, their startled reflex fires, and they dart into a narrow crevice. The lionfish bypasses this reflex by moving so slowly and with such continuous fluidity that it fails to trigger the prey's alarm system. It is like the minute hand of a clock. It is definitely moving, but you cannot perceive the motion until it is too late. As the lionfish closes a distance, it initiates a profound optical illusion. It flares its massive, wing-like pectoral fins outward, extending them to their absolute maximum span. To the human eye, it looks like a display of majesty. To a small fish backed against a wall of coral, it is a localized eclipse. These fan fins are not for swimming. They are tools of spatial manipulation. By spreading them wide, the lionfish completely shatters its own silhouette. The prey can no longer determine where the predator's body begins or ends. The alternating stripes of light and dark act as disruptive camouflage, breaking up the depth perception of the panicked fish. The lionfish appears simultaneously massive and impossible to interpret. In an environment where survival depends on instantly calculating the trajectory of a threat, this visual static induces a fatal cognitive hesitation. The prey's brain stalls, unable to resolve the geometry of the danger approaching it. And this is where the genius of the lionfish's strategy crystallizes. It does not use its fins to trap the prey against the coral. It uses them to gently, almost imperceptibly, herd the prey's instincts. Prey fish rely on recognizing the most viable escape route. When threatened, they look for the path of least resistance. The lionfish, hovering just inches away, subtly adjusts the angle of its flared pectoral fins. It curves them inward slightly, forming a soft, fleshy parabola. It blocks the lateral escape routes, but it deliberately leaves a gap open, a clear line of sight straight ahead. The small fish feels the pressure of the obstruction. Its lateral lines detect the displacement of water. Its vision is overwhelmed by the striped barrier closing in from sides. The coral wall prevents any retreat backward. Panic takes over, and the prey's instincts scream at it to take the only avenue that appears free. It darts forward, choosing the path of least resistance. It is the worst possible choice. The open path is a carefully constructed lie. It leads directly to the center of the lionfish's face. The lionfish has not chased a prey. It has engineered a scenario where the prey willingly swims into its strike zone. And because the prey is moving forward, effectively delivering itself, the lionfish does not need to lunge. It simply needs to open its mouth. With the same devastating biomechanics utilized by the grouper, the lionfish expands its jaws and drops its buccal cavity, creating a localized vacuum. The suction is instantaneous and absolute. The prey, already moving toward the mouth, is accelerated by the sudden collapse of water pressure. It vanishes into the darkness in a fraction of a millisecond. The jaws snap shut. The flared fins relax, folding back into elegant, trailing ribbons. The entire sequence is a masterstroke of energy conservation. The lionfish has expended almost 0 calories to secure its meal. Its slow metabolism, combined with its refusal to chase, means it can survive in environments with very low prey density. It simply drifts to another coral head, flares its fins, and waits for the next nervous fish to make a bad decision. This methodology, using the environment to restrict movement and using psychology to dictate direction, is what makes the lionfish a perfect predator in its native waters of the Indo-Pacific. The prey species have spent millions of years evolving alongside this floating trap. They have learned to recognize the flared fins as a deadly funnel. They keep their distance, and the ecosystem maintains a tense, balanced equilibrium. But the true terrifying efficiency of the lionfish is revealed when it is removed from the context of its evolutionary history. When human activity introduced the lionfish to the waters of the Atlantic and the Caribbean, it unleashed a biological catastrophe. In these new invaded reefs, the prey species do not speak the lionfish's language. A small wrasse or a juvenile snapper in the Caribbean has no genetic memory of the striped, hovering apparition. When a lionfish drifts close and flares its fins, the native prey does not recognize it as a threat. They interpret the extended fins as just another piece of the reef, a soft coral or a harmless sponge. They do not maintain a safe distance. They allow the lionfish to close the gap completely. The trap is set, and because the prey does not know it is a trap, the success rate of the lionfish skyrockets to near-perfect efficiency. The result is an ecological unraveling of staggering proportions, operating with absolute impunity, free from natural predators that recognize its venom, and feeding on a population of naive fish that willingly swim into its mouth. The lionfish consumes everything. It eats the juveniles of commercially vital species. It eats the grazing fish that keep the reef clean of algae, because its stomach can expand to accommodate massive quantities of food. And because its hunting method requires almost no energy, a single lionfish can reduce the juvenile fish population on a coral head by nearly 80% in a matter of weeks. The invasion of the lionfish exposes a profound vulnerability in the architecture of nature. Ecosystems are built on a shared vocabulary of threats and responses. The speed of a shark is countered by the reflex of a fish. The armor of a crab is countered by the crushing jaw of an eel. But the lionfish does not rely on overpowering its prey. It relies on manipulating their decision-making process. And when you introduce a manipulator to a system that has never experienced manipulation, the system simply collapses. To watch a lionfish hunt is to watch a lesson in the architecture of inevitability. It is a creature that has recognized a fundamental flaw in the prey's defense mechanism, the reliance on instinct under pressure. Under extreme stress, an animal stops thinking and defaults to its hardwired programming. It flees away from the solid wall. It turns away from the looming shadow. It chooses a path that looks open. The lionfish has decoded this programming. It does not fight the prey's instinct. It weaponizes it. It turns the very act of escaping into the mechanism of capture. As the currents shift through the mid-depth maze, the lionfish continues its slow, hypnotic drift. Its colors burn brightly against the muted tones of the coral. It looks like an aristocrat taking a leisurely stroll through a ruined city, completely unbothered by the frantic struggle for survival happening all around it. It is not aggressive. It is not angry. It is merely patient. It knows that eventually a small fish will back itself into a corner. It knows that the fish will look for a way out, and it knows that it will gladly provide one. The lionfish does not defeat you by being faster or stronger. It defeats you by making you believe that swimming into its mouth was your own idea. In a world defined by the brutal physics of the chase, the lionfish proves that the most efficient way to win a race is to build a track yourself and let your opponent run straight to the finish line. The coral reef is an environment completely intolerant of the soft and the slow. It is an arena governed by the brutal, uncompromising mathematics of speed, armor, and sharp edges. To survive in the open water above the reef structure, an animal must possess the hydrodynamic architecture required to sprint away from danger, or it must be wrapped in a shell so thick that jaws simply shatter against it. If you lack speed, you must hide. If you cannot hide, you must fight. These are the foundational rules of the ecosystem, written over millions of years of evolutionary pressure. Every sleek shark, every darting wrasse, and every heavily plated crustacean is a living testament to this reality. And then, drifting through the middle of the water column with a lazy, almost staggering incompetence, is the pufferfish. To look at the pufferfish is to look at a biological contradiction, a creature that seems to have completely ignored the design brief for survival. Its body is an awkwardly rounded cylinder, blunt at the front and tapering poorly at the back. It lacks the sweeping, muscular tail that gives other fish their explosive acceleration. Instead, it relies on small, rapidly fluttering pectoral and dorsal fins, propelling itself with a motion that looks more like a frantic hover than a graceful swim. It is entirely unstreamlined. It does not hug the protective contours of the coral, nor does it wedge itself into the deep, dark crevices where the moray eels hide. It wanders openly through the sunlit zones, grazing casually on algae and hard-shelled invertebrates with a heavy, beak-like mouth. Its coloration does not scream danger. It is painted in muted, earthy tones of pale yellow, olive green, and sandy brown, broken by subtle spots or geometric patterns that vaguely resemble the visual noise of the seabed. But it does not stay near the seabed. It floats right in the danger zone, a slow-moving, soft-tissued organism openly advertising its presence to an ocean full of hungry mouths. In a system governed by constant, ruthless predation, the behavior of the pufferfish appears bordering on suicidal. It looks like an easy meal, and that is exactly how it is perceived by the predators that share its waters. From the shadowed edge of the reef, a large predator locks its vision onto the drifting shape. Perhaps it is a barracuda, built for lightning-fast, straight-line interception, or a roaming reef shark, operating on the simple calculation of energy expended versus calories gained. The predator's brain processes the geometry of the pufferfish instantly. It is moving slowly. It has no armor. It is small enough to fit inside the predator's gate. The math is undeniably in the predator's favor. The decision is made, and the predator initiates the strike. It accelerates, closing the distance in a matter of seconds, its jaws opening slightly, the water compressing ahead of its snout. In the ocean, predation is almost always decided in these final, frantic moments. The prey usually realizes it is being hunted and attempts a desperate, last-second maneuver to break the predator's tracking. But the pufferfish does not attempt to flee. It knows it cannot win a race. It knows that attempting to outswim the shadow bearing down on it is a mathematical impossibility. So, instead of turning its tail to run, the pufferfish turns to face the threat, and it initiates a transformation that completely rewrites the rules of engagement. The defense does not begin with an explosion of force. It begins with a mechanical, deliberate gulp. The pufferfish drops its jaw and inhales the ocean. It pumps water rapidly into its mouth and forces it down into a highly specialized, incredibly elastic stomach. This stomach is a marvel of biological engineering. It has lost its primary digestive function, evolving instead into a massive, highly pleated internal balloon. As water is forced inside by the powerful muscles of the fish's throat, the stomach begins to expand, unfolding its pleats and pushing outward against the internal cavity. The physical transformation of the pufferfish is instantaneous and absolute. The skin of the fish is completely devoid of traditional scales. Instead, it is highly elastic, capable of stretching to several times its resting surface area without tearing. In a matter of seconds, the small, awkward, cylinder-shaped fish swells into a massive, rigid, perfectly spherical globe. This shape change serves an immediate geometric purpose. Predators hunt by measuring the size of their prey against the width of their own open jaws. A predator will not attempt to swallow something it cannot physically fit into its mouth, as a blocked airway or a jammed esophagus is a death sentence. By inflating, the pufferfish shatters the predator's initial calculation. The easy, bite-sized meal that existed 3 seconds ago has suddenly tripled in volume. It has become a sphere, and a sphere is the most difficult shape in nature for a hinged jaw to close around. But the inflation does not just change the size of the animal. It deploys a physical armor. Buried within the elastic skin, lying completely flat and invisible when the fish is relaxed, are hundreds of modified scales. As the skin stretches tight over the expanding stomach, these scales are pulled upright. They snap into place with mechanical rigidity, turning the smooth sphere into a bristling, impenetrable pincushion. The predator, already committed to its high-speed strike, slams into this newly formed barricade. Its jaws attempt to clamp down, but they cannot find purchase on the spherical surface. Instead, the soft tissues of the predator's mouth, gums, and throat are met by the unyielding points of the rigid spines. If the predator is aggressive enough or desperate enough, it may try to force the issue, biting down hard in an attempt to crush the inflated ball. The spines drive deep into the sensitive membranes of the attacker's mouth. They are highly structural, designed to wedge themselves into the flesh, making the act of swallowing not just mechanically impossible, but violently painful. The predator is forced to halt his attack, struggling to deal with the spiked obstruction and is just shoved into its own face. However, the physical spikes are merely the first layer of the defense. They are the distraction. They are the mechanical delivery system for a weapon so profoundly devastating that it has shaped the evolutionary history of the entire reef. Embedded within the liver, ovaries, intestines, and specifically the skin of the pufferfish is tetrodotoxin. It is one of the most lethal, fast-acting neurotoxins ever discovered in the natural world, estimated to be over 1,000 times more toxic to vertebrates than cyanide. The pufferfish does not manufacture this toxin itself. It cannot synthesize it from scratch. Instead, it harvests the weapon from the environment. Through its diet of specific algae, invertebrates, and sediment, the pufferfish ingests specialized, symbiotic bacteria that produce tetrodotoxin as a metabolic byproduct. Over millions of years, the pufferfish has evolved a complete immunity to this poison. It absorbs a bacterial toxin, concentrates it within its own organs, and secretes it directly into its skin. It turns its entire body into a toxic sponge. When the predator bites down on the inflated pufferfish, the spines puncture the predator's mouth, creating open wounds. The extreme pressure of the bite simultaneously crushes the pufferfish's skin against the predator's highly vascular oral membranes. The tetrodotoxin is transferred directly into the predator's bloodstream. The venom does not act by destroying tissue or causing localized necrosis. Its method is far more elegant and far more terrifying. Tetrodotoxin is a precise, molecular key designed to fit perfectly into the voltage-gated sodium channels of nerve cells. In a healthy nervous system, these sodium channels open and close, allowing electrical signals to jump from the brain, down the spinal cord, and into the muscles, telling them to contract, to move, to breathe. Tetrodotoxin acts as a microscopic cork. It wedges itself into the sodium channels and absolutely blocks the flow of electricity. For the predator with the pufferfish in its mouth, the effect is almost instantaneous. The pain from the spines is suddenly eclipsed by a profound, terrifying numbness. The sensation spreads rapidly from the lips and gums, radiating backward into the jaw and throat. The predator's brain screams commands at its muscles: bite down, swallow, spit out, pull away. But the muscles do not receive the message. The electrical wires have been cut. A profound muscular dysfunction sets in. The predator's jaw goes slack, unable to maintain the force required to crush the shell or hold the fish. Disorientation overwhelms the attacker as the toxin begins to systematically shut down its peripheral nervous system. If a large enough dose is absorbed, the paralysis will quickly reach the diaphragm, stopping the respiratory system entirely, leading to asphyxiation while the animal is still completely conscious. But in the vast majority of interactions on the reef, death is not the outcome, and it is not the goal. Evolutionary biology does not reward unnecessary killing. It rewards survival. The predator, experiencing the sudden, terrifying failure of its own nervous system, is gripped by a biological panic that supersedes all hunger. Its jaw relaxes involuntarily. It shakes its head violently, desperately trying to dislodge the spiked, toxic sphere from its mouth. It backs away, coughing, gagging, its motor function stuttering as it struggles to clear the neurotoxin from its system. The predator releases the pufferfish, not out of a conscious decision of mercy, but out of absolute, alarming physiological failure. The reef absorbs the end of the interaction in silence. There is no triumphant pursuit, no bloody finale. The predator retreats into the deeper water, its body trembling, its mouth numb, its heart racing as it metabolizes the poison. It will survive, but it will be forever altered. This is the true brilliance of the pufferfish's strategy. It does not exist to kill the things that try to eat it. It exists to educate them. Predators possess highly developed associative memories. A shark or a grouper that survives a mouthful of tetrodotoxin and the agonizing puncture of defensive spines will never, under any circumstances, forget the experience. The visual cue of the slow-moving, awkwardly swimming, pale-colored fish is permanently burned into predators' neural pathways, forever linked to the sensation of numbness, paralysis, and near death. By allowing itself to be attacked, by surviving the initial bite to mechanical inflation, and by punishing the attacker with a non-lethal but terrifying dose of neurotoxin, the pufferfish effectively inoculates the predator against its entire species. That specific predator will now actively avoid any pufferfish it encounters for the rest of its life. This localized learning spreads through the ecosystem. As more predators make the mistake of biting a pufferfish and survive to remember the agony, a collective avoidance behavior settles over the reef. The pufferfish population as a whole benefits from the chemical trauma inflicted on the predators. The toxic shield extends beyond the individual, creating a psychological safe zone for every pufferfish in the area. They are granted the freedom to graze openly, to swim slowly, and to ignore the rules of speed and camouflage because their predators have been trained to ignore them. But this incredible defense mechanism comes with severe energetic cost, which is why it is used so sparingly. As the traumatized predator vanishes into shadows, the pufferfish remains suspended in the water column, still fully inflated, a rigid, spiked ball drifting with the current. It holds its posture for several long minutes, ensuring that the threat is truly gone, that no secondary predator is waiting to strike while it is vulnerable. Inflation is not a state the pufferfish can maintain indefinitely. The massive intake of water compresses its internal organs, restricting its ability to digest food and severely limiting its mobility. An inflated pufferfish is largely at the mercy of the ocean currents, unable to steer or propel itself with any real efficiency. It has sacrificed all of its maneuverability for the sake of absolute defense. When it is finally convinced that the danger has passed, the reversal begins. The process is slow and highly vulnerable. The strong sphincter muscle at the top of the stomach relaxes. The pufferfish begins to forcefully expel the water back out through its mouth and gills. The rigid, spherical shape begins to deflate, the skin losing its extreme tension. As the volume decreases, the upright spines unlock and fold backward, laying flat once more against the soft, scaleless skin. The animal shrinks, the pleats of its stomach folding back into their dormant state. Within minutes, the transformation is complete. The impenetrable, toxic fortress collapses back into the form of a soft, clumsy, unremarkable fish. It rights itself in the water column, its small pectoral fins fluttering rapidly to regain its balance. It does not dart away in fear. It simply turns its attention back to core below and resumes its slow, deliberate search for food, picking at the algae and crushing small shells with its beak. Nothing about its posture or its behavior suggests the violence that just occurred. It moves through the ecosystem as a quiet, unassuming contradiction. It is a creature that holds the power to silence the nervous system of a giant, yet it spends its days grazing peacefully on the rocks. The pufferfish survives not by outrunning its enemies and not by overpowering them with brute strength. It survives through the deployment of a perfect, graduated consequence. It waits for the predator to commit. It mechanically removes the option of consumption, and then it delivers a chemical punishment that guarantees a mistake will never be repeated. It wins the arms race of the ocean by ensuring that any attention it receives is instantly transformed into an eternity of regret. As the reef descends, the fundamental rules of survival undergo a claustrophobic shift. The open, sunlit terraces where speed and agility dictate the hierarchy of life slowly give way to a darker, more complex geometry. Coral heads stack violently atop one another, their foundations undercut by centuries of shifting currents, creating a densely packed lattice of fissures, dead-end caves, and narrow, shadow corridors. Down here, the water does not flow freely. It is forced through cracks, slowing down, carrying the heavy sense of the ecosystem in concentrated streams. In this fractured terrain, the advantage of a powerful tail or a streamlined body vanishes completely. Open water predators do not enter these slots. There is no room to turn, no space to accelerate, no distance to build the momentum required for a strike. To the small, heavily armored creatures of the reef, these deep crevices represent the ultimate sanctuary. A lobster backs into a hole, trusting its thick exoskeleton to block the entrance. A startled reef fish darts into a limestone crack, pressing its body against the unyielding stone, confident that whatever was chasing it cannot follow. They rely on the assumption that predators require open space to operate. They assume that if the walls are tight enough, the danger is locked outside. But the reef is not a place of guaranteed sanctuary. The dark holes do not just offer shelter from the ocean. Sometimes, the holes are watching you. If you stare into the absolute blackness of a coral fissure, the darkness occasionally betrays a texture. It does not look like an animal at first. It looks like a jagged continuation of the reef itself, a mottled, irregular stone wedged deep within the throat of the cave. But then, the stone shifts. A slow, rhythmic pulsing begins. The shadows part, revealing an elongated snout and a jaw that opens and closes with steady, unhurried cadence. Inside the mouth, catching the faint ambient light, is a horrifying palisade of long, recurved, glass-like teeth. The moray eel is not hiding in the reef. It is wearing the reef like a suit of armor. To encounter a moray in its element is to confront a creature that has completely discarded the standard blueprint of a fish. It has no pelvic or pectoral fins to speak of. It lacks the rigid, armored scales that protect the vast majority of marine life. Its body is a continuous, serpentine ribbon of pure, hyperdense muscle, laterally compressed to slide effortlessly through gaps no wider than its own skull. Covering this muscular cord is a thick, highly specialized layer of mucus. This slime coat is not merely biological byproduct. It is a critical adaptation. It serves as an extreme lubricant, allowing the eel to slither forward and backward over razor-sharp coral and abrasive limestone without suffering a single scratch, while simultaneously acting as a chemical barrier against the infections that fester in stagnant caves. Everything about the moray is optimized for extreme confinement. In open water, a moray is surprisingly vulnerable. It's undulating. Snake-like swimming motion is inefficient for long-distance travel and is easily outpaced by sharks or large pelagic hunters. But the moray has no interest in the open water. It has traded the freedom of the ocean for absolute supremacy within the cracks. The gaping, tooth-filled mouth that protrudes from the darkness is universally interpreted by humans as a display of aggressive malice. It looks like a predator panting, waiting for the moment to strike. But this is a profound misunderstanding of eel anatomy. The moray is not snarling. It is simply breathing. Unlike fast-swimming fish that force water over their gills simply by moving forward, the moray spends its life stationary in cramped spaces with poor water circulation. Its gills are located far back behind its head, reduced to small, circular openings. To breathe, the eel must actively and continuously pump water into its mouth, over the gills and out the back. The terrifying grin is a physiological necessity, an endless respiratory rhythm born of confined spaces it inhabits. But while the open mouth is not a threat display, it is undeniably a loaded weapon. The moray does not patrol the reef looking for victims. It operates on the principle of minimal energy expenditure. It weaves its long body deep into the interlocking chambers of the coral, anchoring its tail securely around a limestone pillar deep inside the rock. It only extends its head and the first few inches of its neck out to the threshold of the cave. And then it waits. Vision is secondary down here in the shadows. The eel's eyes are small and its eyesight relatively poor. Instead, it perceives the world through chemistry. Projecting from the tip of its snout are highly developed olfactory tubes. The moray tastes the water, reading the chemical trails carried by the slow currents. It can detect the scent of a wounded fish, the stress pheromones of an exhausted crab, or the subtle biological signature of a healthy prey animal simply drifting too close to the cave entrance. It reads these signals like a detailed map, calculating the exact proximity and trajectory of the target without ever needing to see it clearly. The psychological tension of the reef edge is defined by these unseen boundaries. A fish swims past a dark opening, unaware that a pair of chemical sensors has just locked onto its trail. The eel does not tense or coil. It remains perfectly still, blending into the rock, allowing the prey to inch closer. It waits for the fish to cross a very specific, invisible threshold. It waits until the distance between its jaws and the prey is shorter than the time it takes for a nerve signal to trigger a startle reflex. When the strike comes, it shatters the stillness with terrifying violence. The moray lunges forward from the crevice with explosive acceleration. The jaws snap shut with bone-crushing force, the recurved teeth sinking deep into the flesh or locking securely around a hard-shell crustacean. But this is where the moray's hunting strategy fundamentally diverges from almost every other predator on the reef. When a shark or a grouper strikes, the goal is usually to overpower the prey in the open water, shaking it or inhaling it until the struggle ends. The moray does the exact opposite. The moment its jaws lock onto the target, the eel throws itself into rapid reverse. It uses a powerful musculature anchored deep inside the cave to violently yank the captured prey backward, dragging it out of the open water and pulling it directly into the suffocating darkness of the hole. This backward retreat is the true genius of the moray eel. The eel understands implicitly that it does not need to win a wrestling match in the open ocean. It only needs to get the prey inside the cave. Once the prey is dragged across the threshold, the physics of the encounter change completely. In the open water, a struggling fish can use its tail to generate thrust. A crab can use its legs to push away. But inside the narrow, jagged confines of the coral fissure, there is no space to maneuver. The prey cannot turn around. It cannot accelerate. Its fins scrape uselessly against the stone walls. The architecture of the reef, which moments ago seemed like a sanctuary, is instantly transformed into a straitjacket. The moray uses the walls of the cave as an extension of its own body. As the prey thrashes, the eel presses the victim against a jagged rock, using the environment to pin it down, completely neutralizing any defensive leverage the animal might have had. The eel does not need to overpower the prey with brute strength alone. It lets the stone do the holding. But dragging a live, struggling animal into a tube barely wider than your own body presents a massive anatomical problem. Most predatory fish swallow their prey by creating a powerful vacuum, opening their mouths wide to suck the food down their throats. A moray eel cannot do this. Because it is wedged inside a tight cave, it cannot expand its head or neck enough to generate a suction vortex. Furthermore, if it loosens its primary bite to reposition the struggling prey, the victim might slip free and escape back out the front of the cave. Evolution solved this problem with a mechanism that is truly the stuff of nightmares. Deep within the throat of the moray eel, resting behind the primary skull, is a second, completely distinct set of jaws. These are the pharyngeal jaws. They are fully equipped with their own terrifying array of sharp, backward-pointing teeth. While the primary jaws remain locked in a death grip on the front of the prey, the eel's internal musculature activates. The pharyngeal jaws literally detach from their resting place and throat and launch forward, sliding up through the mouth cavity. They reach out, bite down firmly on the prey behind the primary jaws, and lock on. Then, the primary jaws release for a fraction of a second, and the pharyngeal jaws retract, violently yanking the prey backward into the esophagus. It is a biomechanical conveyor belt of extraction. The eel does not swallow its food. It ratchets it down its own throat. This horrifying dual-jaw system allows the moray to consume large, struggling prey entirely within the confines of a narrow cave. It can dismantle a heavy-shelled lobster or swallow a large parrotfish without ever needing to expose itself to the open water. It breaks the prey down not by tearing it to pieces, but by systematically dragging it inward, millimeter by millimeter, until the struggle simply ceases in the darkness. This method of predation casts a long, invisible shadow over the entire ecosystem. The reef is mapped by fear, and the territories of large moray eels are well documented by the surrounding fish. Grazers and foragers learn to maintain a strict distance from the rock faces, avoiding the blind corners and the jagged undercut ledges. They recognize that the reef is not just a structure to swim over. It is a porous entity filled with teeth. Yet, the moray is not the mindless, aggressive monster of maritime folklore. It does not actively seek out conflict with creatures it cannot eat. When divers or snorkelers are bitten by moray eels, it is almost never an unprovoked attack. It is a result of a human hand blindly reaching into a dark hole, searching for a lobster or a shell. To the eel, a hand invading its sanctuary is indistinguishable from a threat or a meal. The eel reacts exactly as it was designed to, with a lightning-fast clamp of the primary jaws and an immediate backward pull. The severity of moray bites often comes not from the eel tearing the flesh, but from a human violently jerking their hand backward against the heavily recurved teeth, turning a puncture wound into a deep, ragged laceration. In its natural context, the moray is a creature of profound patience and mechanical perfection. It has found the one weakness in the armor of the reef. It recognized that the very spaces prey animals use to escape danger could be turned into inescapable traps. As the ocean currents sweep past the dark entrance of the fissure, the eel slowly finishes its meal. The primary jaws relax. The pharyngeal jaws retract to their dormant position deep in the throat. The steady, rhythmic panting of the mouth resumes, drawing fresh water over the gills. The eel settles back into the coils of its own muscle, its body perfectly conforming to the jagged contours of the limestone. It waits for the next scent to drift through the water. It does not need to swim. It does not need to hunt. It only needs to breathe and wait for the ocean to deliver the next victim to the edge of the shadow. The moray eel proves that you do not need to be the fastest creature in the sea to be its most inescapable killer. You simply need to understand that when the walls close in, speed no longer matters. The cave is the weapon. The eel is merely the teeth that close the door. There is a distinct transition point in the topography of the reef where the delicate, branching structures of the upper gardens are pulverized by the relentless kinetic energy of the ocean. The soft sands are scoured away, leaving behind a harsh, abrasive landscape known as a rubble zone. This is the reef's testing ground for durability. It is a mosaic of fractured limestone, shattered shells, and coarse gravel, continuously ground down by wave surge and tidal currents. Soft-bodied animals do not survive long here. In this abrasive environment, evolution overwhelmingly favors the heavily armored. Crabs, snails, and bivalves dominate the terrain, encased in thick, calcified exoskeletons built to withstand crushing pressure and violent impacts. To wander the rubble zone is to walk through a fortress of living stones. The underlying biological assumption here is that if your shell is thick enough, you are exempt from the violence of the food web. But hiding within this fortress of broken rock is an animal that does not respect the authority of armor. It is a creature that has effectively bypassed the biological limitations of muscle and bone, choosing instead to weaponize the fundamental laws of physics. If you scan the rubble carefully, you will notice that not all the holes in the seafloor are natural. Some are perfectly cylindrical, reinforced at the edges with carefully selected pieces of shell and coral debris. This is not a random hiding place. It is a meticulously engineered bunker, and resting just inside the threshold of this burrow, monitoring the world with an alien, vibrating intensity, is the mantis shrimp. To look at a mantis shrimp is to experience a visual contradiction. In a landscape defined by muted grays and browns, the mantis shrimp is a riot of impossible color. It is banded in electric greens, deep reds, and iridescent blues, looking less like a marine predator and more like a brightly painted mechanical toy. But its flamboyant appearance is a distraction from the terrifying sophistication of its anatomy. The first thing that registers are the eyes. They are mounted on mobile, independent stalks, constantly whirring and rotating, tracking multiple targets simultaneously in different directions. But the mechanical movement of the eyes is nothing compared to what they are actually processing. A human eye contains 3 types of color-receptive cones. The eye of the mantis shrimp contains 16. It does not simply view the reef. It analyzes it on a spectrum completely incomprehensible to the mammalian brain. It sees deep into the ultraviolet range. It perceives the intricate, invisible bands of circularly polarized light bouncing off the scales of passing fish and the shells of hidden crabs. It can look at a seemingly uniform expanse of sand and instantly isolate the exact chemical signature of a living organism buried beneath it. The mantis shrimp's vision strips away the camouflage of the ocean. In an environment where seconds dictate survival, this sensory array gives the mantis shrimp a godlike tactical advantage. It knows exactly what you are, exactly where you are, and exactly what you're made of long before you even realize you are being watched. But the eyes are merely the targeting system. The true terror of the mantis shrimp lies folded neatly beneath its brightly colored chest. A large, heavily armored crab picks its way across the rubble. It moves with the slow, deliberate confidence of an animal that knows it is practically invincible. Its carapace is thick, fortified with layers of calcium carbonate that have deflected the bites of moray eels and the crushing jaws of triggerfish. It fears nothing in the rubble zone because its evolutionary programming tells it that its shell is a mathematical guarantee of safety. It scuttles closer to the reinforced perimeter of the burrow, unaware that it has just been locked onto by the most complex visual system on the planet. The mantis shrimp does not leave its bunker. It does not need to expose its body to the open ocean. It only needs a crab to come within a few inches of its threshold. Tucked beneath the shrimp's head is a pair of highly specialized raptorial appendages. In the smashing species of mantis shrimp, the joints of these arms do not end in claws or pincers. They end in dense, calcified clubs shaped like the blunt end of a hammer. As the crab enters the strike zone, the mantis shrimp does not wind up. It does not pull its arms back to generate momentum, because pulling back would alert the prey and waste precious time. Instead, it relies on a biological mechanism that functions exactly like a loaded crossbow. Inside the arm is a specialized, saddle-shaped spring made of highly elastic chitin. Powerful muscles contract, locking a tiny biological latch in place, and then pull against the spring, compressing it, storing a massive amount of potential elastic energy. The shrimp is not getting ready to hit. It is winding a bomb. The crab pauses, its antennae twitching. The mantis shrimp releases a latch. What happens next is widely considered one of the fastest movements in the entire animal kingdom. The compressed spring violently unloads, driving the calcified club forward. The acceleration is so extreme that it defies the resistance of the water. The club reaches speeds exceeding 50 miles per hour, accelerating faster than a .22 caliber bullet, leaving the barrel of a gun. The club slams into the thick carapace of the crab. The mechanical impact alone is devastating, delivering hundreds of pounds of localized force in a fraction of a millisecond. The thick, unyielding shell of the crab is instantly compromised, spiderwebbing with microfractures as the kinetic energy violently disrupts its structural integrity. But if the mantis shrimp only delivered a devastating physical blow, it would merely be an incredibly strong animal. The true horror of the strike, the reason the mantis shrimp is a predator without parallel, occurs in the microscopic wake of the club. Because the appendage is moving through the water so incredibly fast, the water simply cannot get out of the way fast enough. The club literally tears the water molecules apart, creating a localized drop in pressure so extreme that the water behind the club instantly boils at room temperature. This creates a tiny vapor-filled void known as a cavitation bubble. This bubble exists for only a few millionths of a second. The immense pressure of the surrounding ocean instantly crushes it, forcing the bubble to collapse in on itself. The collapse of a cavitation bubble is a catastrophic physical event. When the void snaps shut, it generates a secondary shockwave that slams into the crab just a microsecond after the physical club hits. The implosion is so violent that it generates temperatures on par with the surface of the sun, over 8,000 degrees Fahrenheit, inside the microscopic core of the bubble. It emits a brief, intense flash of light, a phenomenon known as sonoluminescence. The mantis shrimp is not just hitting the crab. It is hitting the crab, and then the physics of the ocean is detonating a concussive bomb against the crab's shell immediately afterward. This double strike is the ultimate armor breaker. Even if the crab's thick shell somehow manages to absorb the initial physical impact of the club without completely shattering, the secondary shockwave from the cavitation collapse ripples directly through the calcium carbonate. The shockwave ignores the external armor, propagating to the shell and liquefying the soft, internal tissues of crab beneath it. The crab's defense is completely bypassed. It is killed by the sheer concussive force of the pressure wave before the physical hole in its shell even matters. The mantis shrimp quickly retracts its arm, the biological spring already resetting, the latch locking back into place. The entire interaction, the unspooling of the spring, the physical strike, the cavitation collapse, and the retraction has occurred in under 3 milliseconds. It is so fast that human eyes cannot perceive it without high-speed cameras. To a human observer, there is only a sudden, sharp crack that echoes through the water, and then the crab is simply broken. The mantis shrimp reaches out, grabs the shattered remains of crab, and drags it down into the dark safety of its burrow to feed. This level of localized, catastrophic violence requires an anatomy that is just as resilient as it is destructive. The force generated by the strike is so immense that, theoretically, the mantis shrimp's own arm should shatter upon impact. But the club is a masterpiece of shock absorption. It is constructed from microscopic, spiraling layers of mineral called hydroxyapatite, the same mineral that makes human teeth hard, layered over a shock-absorbing core of elastic chitin. The spiral structure acts like a coiled mattress spring, taking the immense force of the recoil and dispersing it safely through the appendage, preventing microfractures from spreading and destroying the shrimp's own weapon. Scientists study the microscopic structure of the mantis shrimp's club to design lighter, more resilient body armor and reinforced materials for aerospace engineering. From an ecological perspective, the mantis shrimp reigns as an invisible tyrant of the rubble zones. Because it has the ability to easily dismantle heavily armored prey, it exerts a massive top-down pressure on the populations of snails, crabs, and bivalves. It dictates the architecture of the local food web, ensuring that no species can rely entirely on simply growing a thicker shell. But this overwhelming power comes with a strict behavioral limitation. The mantis shrimp is tied to its burrow. Unlike roaming predators that can patrol massive territories, the mantis shrimp is an ambush specialist. It relies on the security of its bunker to protect its softer, unarmored abdomen, and it needs a solid foundation of the hull to brace against the massive recoil of its own strike. It cannot wander the open reef, firing its clubs randomly. It is a creature defined by a terrifyingly specific geometry. If you stay out of range, you are perfectly safe. If you cross the invisible line of its threshold, you are subjected to the most violent mechanical force in the ocean. This turns a rubble field into a psychological minefield for the animals that live there. The heavily armored grazers learn to recognize the neatly organized entrances of the mantis shrimp burrows. They alter their foraging routes, giving the holes a wide, respectful berth. They understand that there are certain patches of the seabed where their armor is completely meaningless. The mantis shrimp does not need to chase its prey. It simply relies on the arrogance of the armored, waiting for a crab that believes its shell is thick enough to save it. As the sun shifts over the reef, casting long shadows across the broken limestone, the mantis shrimp remains perfectly still in its doorway. Its kaleidoscopic eyes whir and pivot, pulling in the polarized light, analyzing the chemical trails, stripping away the secrets of the surrounding water. It does not posture. It does not display aggression. It is the size of a human forearm, yet it sits with the absolute, unquestionable confidence of an apex predator. It is a creature that represents the extreme, illogical limits of evolutionary adaptation. It proves that in the endless arms race of the ocean floor, biology does not always respond to a thicker shield by building a sharper tooth. Sometimes, evolution decides to rewrite the rules entirely. The mantis shrimp does not bother with venom, and it does not bother with teeth. It simply turns the water itself into an explosive projectile. It stands at the entrance to its home, a tiny, colorful architect of destruction, patiently waiting for the next victim to learn that in the face of absolute velocity, armor is nothing more than shrapnel waiting to happen. The architecture of the reef is not uniform. While the sunlit upper terraces are defined by open space and the freedom of movement, the deeper you go, the more the environment begins to close in on itself. The coral formations grow denser, stacking and fusing under the weight of the water. Wide avenues narrow into twisting corridors. Corridors constrict into shadowed fissures, and fissures terminate in pitch-black, dead-end crevices. In this three-dimensional labyrinth, the physics of survival undergo a radical transformation. In the open ocean, the ultimate currency is speed. A tuna or a shark relies on the explosive forward thrust of a massive tail to run down its prey, but speed requires clearance. In the claustrophobic crush of the deep reef interior, a torpedo-shaped body is a fatal liability. You cannot sprint through a keyhole. The fish that live within these tight, limestone vaults understand this geometry intimately. They survive by wedging themselves into spaces where the larger, faster predators simply cannot follow. They operate on the assumption that if the walls are tight enough and the ceiling is low enough, they are immune to the violence of the world outside. They trust the rock to protect them, but the rock is compromised, sifting through the cracks, moving with a fluid, terrifying grace that defies the jagged angles of the coral. It is a predator that does not fight the labyrinth. It becomes it. The arrival of the sea snake is a masterclass in understatement. It does not announce itself with the heavy displacement of water or the frantic thrashing of fins. It simply pours into the frame, a continuous, laterally compressed ribbon of muscle and scale. Its body is profoundly elongated, an evolutionary adaptation that sacrifices the ability to accelerate rapidly in open water for the absolute mastery of confined space. The tail, flattened vertically into a perfect, paddle-like rudder, sculls with gentle, rhythmic strokes. The rest of the body follows in smooth, undulating waves, flowing over the abrasive limestone with frictionless ease. The head is startlingly narrow, barely wider than the neck itself, tapering to a blunt snout. This anatomy allows the sea snake to infiltrate the deepest, most inaccessible sanctuaries on the reef, where a grouper gets stuck, and a shark wouldn't even attempt entry. The sea snake simply glides forward, threading the needle of the coral with quiet inevitability. Yet, the most remarkable feature of the sea snake is not its shape, but its relationship with the water itself. Unlike every other predator that hunts in the deep crevices, the sea snake is an air breather. It is a descendant of terrestrial reptiles, bound by biology to return to the surface to fill its lungs. In a purely aquatic environment, this should be a massive disadvantage, a ticking clock that limits its ability to hunt and exposes it to danger every time it ascends. But evolution has transformed this apparent vulnerability into a devastating tactical weapon. The sea snake's lung does not sit compactly in its chest like a mammal's. It extends down almost the entire length of its elongated body. This massive, tubular organ certainly stores oxygen for prolonged dives, but its primary function during a hunt is far more sophisticated. The lung acts as a highly calibrated, internal buoyancy compensator. By shifting the distribution of air within this long chamber, the sea snake can micro-adjust its position in the water column without moving a single muscle. When a fish hovers, it must constantly flutter its pectoral fins to prevent itself from sinking or rising, creating tiny pressure waves that broadcast its presence. The sea snake does not need to flutter. It fine-tunes its internal air volume and achieves absolute zero-gravity suspension. It hangs in the water column like a phantom. It does not swim into a crevice. It simply drifts into it, carried by an invisible adjustment of gravity. Furthermore, many species of sea snake had developed the extraordinary ability of cutaneous respiration. They can literally breathe through their skin, absorbing dissolved oxygen directly from the surrounding seawater and venting carbon dioxide. This extends their dive times to staggering lengths, sometimes hours at a time. The ticking clock is silenced. The snake has all the time in the world. As it pushes deeper into the lightless maze of the reef, the sea snake abandons its vision. In the cramped, twisting tunnels, eyes are virtually useless. Instead, the snake navigates and hunts entirely through chemistry. The head probes forward, and a specialized, forked tongue flicks out into the water. It is tasting the ocean, sampling the microscopic chemical cues suspended in the fluid. Every living thing on the reef constantly sheds a molecular exhaust. The proteins from a beating gill, the stress hormones of resting fish, the biological static of life. The snake's tongue catches these molecules and drags them back into the Jacobson's organ in the roof of its mouth. The snake is reading the unseen world. It detects a concentrated chemical trail leading into a narrow, dead-end fissure. A small reef fish is tucked deep inside, pressed hard against a stone. The fish is safe from the jaws of the moray and the suction of the grouper, but it is not safe from the chemistry. The sea snake advances. Its movements are agonizingly slow, completely devoid of predatory urgency. It does not want to trigger the prey's lateral line sensors, which detect changes in water pressure. It wants to arrive as a ghost. The distance closes. The narrow head of the snake rounds the final corner of the crevice. The prey fish suddenly registers the intrusion. The visual of the predator is right in front of it. The instinct to flee is overwhelming, but the geometry of the sanctuary has become a trap. There is nowhere to dart. There is no open water to accelerate into. The fish can only press itself tighter into the rock, trapped by the very walls it trusted. The strike of the sea snake is not a spectacle. It is not the violent, thrashing ambush of a crocodile or the coiled, explosive lunge of a rattlesnake. In a space this tight, a dramatic lunge is physically impossible. Instead, the strike is a marvel of brutal economy. The snake's head simply snaps for a fraction of an inch. The small jaws open, the fangs deploy, and they clamp down onto the flesh of the trapped fish. The contact lasts for less than half a second, and then the snake does something that seems to defy every rule of predation. It lets go. It does not hold the prey. It does not attempt to drag the struggling fish out of the hole. It does not wrap its muscular coils around the victim to crush the life out of it. The moment the bite is delivered, the sea snake throws itself into reverse, sliding its body smoothly backward out of the crevice, retreating down the corridor it just navigated. To an observer unfamiliar with the mechanics of marine venom, this looks like a failure. It looks as though the predator struck, lost its grip, and gave up. The prey fish remains in its hole, completely intact, bearing only a microscopic puncture wound. It seems as though it has survived, but the sea snake has not failed. It has simply outsourced the violence. By releasing the prey immediately, the sea snake completely negates the risk of physical injury. Reef fish are armed with sharp dorsal spines, powerful gills, and desperate energy. If the snake tried to hold on and wrestle the fish in confined space, it would risk being blinded, sliced open, or having its jaw broken by the thrashing prey. The snake refuses to engage in a physical struggle because it knows that the fight is already over. The venom injected during that fraction of a second is among the most lethal substances in the global ocean. It is an incredibly dense, highly refined cocktail of neurotoxins, perfectly calibrated to dismantle the vertebrate nervous system. The venom does not destroy tissue. It does not cause massive internal bleeding or dramatic, localized necrosis. Its method is silent, cold, and entirely systemic. The neurotoxins race through the prey's bloodstream, actively seeking out the neuromuscular junctions, the critical bridges where the brain's electrical signals meet the muscle fibers. When the toxins reach these junctions, they bind to the receptors, acting as an impenetrable chemical blockade. The brain continues to scream commands, swim, fight, breathe, but the signals hit a dead end. Inside the dark crevice, the prey fish experiences a terrifying, creeping stillness. It is not overwhelmed by pain. It is overwhelmed by an inability to respond. The powerful muscles of its tail begin to falter. The pectoral fins, essential for maintaining balance, go slack. The fish attempts to push against the stone, but its body refuses to obey. This is the true horror of the sea snake's venom. It does not kill by brute force. It kills by subtraction. It slowly unplugs the animal from its own anatomy. As the paralysis deepens, the most critical failure occurs. The muscles that operate the gills, the ones responsible for drawing oxygen-rich water over the respiratory membranes, begin to stutter. The fish is suffocating, fully conscious, completely immobilized within its own chosen sanctuary. Down the corridor, waiting patiently in the shadows, the sea snake monitors the situation. It flicks its tongue, reading the chemical changes in the water. It can taste the exact moment the prey's metabolism begins to crash. It can taste the cessation of movement. It waits without an ounce of anxiety, suspended perfectly in the water column by its elongated lung. It knows that venom is a tool of certainty. It removes the variables of the hunt. It takes the chaos of a struggle and reduces it to a quiet, mathematical conclusion. When the chemical signals indicate that the prey is completely incapacitated, the sea snake begins its second approach. It flows back down the twisting corridor, rounding the corner to find the fish exactly where it left it. The prey is still alive, its eyes seeing the predator return, but its body is a statue. There is no resistance now. The sea snake opens its highly flexible jaws, unhinging the necessary bones to accommodate the width of the fish. It begins to swallow the prey head first, working the immobilized body down its throat with slow, methodical muscular contractions. The tight walls of the crevice, which offer the fish no room to fight, now provide the snake with the leverage it needs to push the meal down its elongated stomach. This is the perfection of the bite and retreat strategy. It is predation stripped of all drama, reduced to a perfectly executed chemical transaction. The ecological impact of the sea snake is profound, yet almost entirely invisible. It is a precision instrument, shaping the behavior of the reef from within the rock itself. Its presence fundamentally alters the value of shelter. For millions of years, the deep crevices were the ultimate safe zones. The sea snake turns those safe zones into liabilities. The fish that inhabit the reef must constantly balance the fear of the open water, where the fast predators roam, against the terror of the cracks, where the silent chemistry waits. It creates a psychological tension that dictates where animals sleep, where they forage, and how they navigate the complex topography of their home. And despite its terrifying lethality, the sea snake is a creature of profound indifference toward anything it does not intend to eat. For humans, an encounter with a sea snake often triggers an innate, primal panic. The human mind associates a venomous serpent with aggressive, striking hostility. But the sea snake does not view a human as prey, and it rarely views a human as a threat. Its venom system, its fangs, its entirely specialized hunting methodology are designed exclusively for small fish trapped in small holes. Divers frequently report sea snakes swimming directly up to them, flicking their tongues against a diving mask or wrapping gently around an arm. This is not aggression. It is curiosity. The snake is simply using its chemical sensors to map a large, unfamiliar object in its environment. Because its fangs are situated far back in its relatively small mouth, and because its instinct is to bite only what it can swallow, offensive strikes on humans are incredibly rare. When bites do occur, they are almost exclusively the result of the snake being violently grabbed, stepped on, or hauled out of the water in a fishing net. Even then, the snake will often deliver a dry bite, striking without expending its precious venom, viewing the venom as a tool for hunting rather than a shield for defense. The danger to humanity is real, but is born of accident, not malice. As the sea snake finishes its meal, the bulk of the fish visible as a slight bulge in its streamlined body, it slowly begins to back out crevice. It needs to breathe. It navigates a labyrinth, flowing upward to the narrowing corridors, leaving the dark, heavy architecture of the lower reef behind. It breaks out into the sunlit shallows, a ribbon of banded color rising smoothly toward the surface. It breaks the tension of the ocean, exhales the stale air, and draws a deep, vital breath of the atmosphere. For a brief moment, it is suspended between two worlds, the bright, chaotic expanse of the air and the dense, structural lethality of the reef. Then, with a silent flick of its paddle-shaped tail, it slips back beneath the surface. It adjusts the volume of its lung, finds its perfect, frictionless buoyancy, and descends once more into the labyrinth. It does not rule the reef with a heavy hand. It leaves no shattered shells, no clouds of blood, no panicked schools of fish fleeing in its wake. Its dominance is quiet, absolute, and woven directly into the nervous systems of the things it hunts. In the tightest corners of the ocean, where the rules of speed and strength no longer apply, the sea snake proves that the most terrifying predators are the ones that simply touch you, walk away, and let your own biology do the killing. The periphery of the coral reef is defined by a brutal, unyielding architecture. As the vibrant, delicate branching corals of the upper sunlit zones give way to the deeper, colder slopes, the environment trades soft beauty for hard edges. This is a landscape built from the compressed skeletons of millions of generations of polyps, fractured by the relentless pounding of storm surges, and bound together by encrusting algae into solid, unforgiving limestone. It is a world of sheer walls, deep vertical fissures, and heavy, overlapping slabs of rock. In this unforgiving terrain, speed is a luxury few can afford, and camouflage is often insufficient against predators that hunt by scent and vibration. Here, the ocean demands a different kind of survival strategy. It demands endurance. It demands the ability to withstand immense physical trauma. In a world defined by crushing jaws and tearing teeth, one creature has chosen to meet force with absolute, unyielding resistance. Moving across the broken rubble with a heavy, mechanical certainty is the lobster. It does not glide. It does not swim. It walks, dragging its weight across the ocean floor like a siege engine crawling across a battlefield. The lobster has entirely abandoned the concept of evasion. It has accepted that it will be seen, that it will be targeted, and that it will be struck. Its entire evolutionary philosophy is based on the premise that when the strike finally comes, it simply will not matter. To look at the lobster is to look at a biological fortress. Its body is entirely encased in a massive, articulated exoskeleton, heavily reinforced with layers of chitin and heavily calcified proteins. This is not a thin shell. It is thick, rigid, and engineered to disperse kinetic energy across its surface. Every segment of its body, from the heavy carapace shielding its vital organs to the overlapping, segmented plates protecting its muscular tail, is designed to turn aside the teeth of the reef's most aggressive hunters. It is a creature wearing plate armor in an environment where almost everyone else is naked. But armor alone is passive. To survive, the fortress must also be armed. Raised slightly as the lobster navigates the uneven terrain, held in a state of constant, sweeping vigilance, are two massive claws. They are rarely symmetrical, revealing a sophisticated division of labor. One claw is the crusher. It is oversized, blunt, and heavily reinforced with thick, molar-like nodules. It is built for raw, overwhelming compression. The lobster uses its claw to slowly, methodically shatter the thick shells of sea snails, clams, and bottom-dwelling crabs, applying a slow-building pressure until the victim's armor catastrophically fails. The other claw is a cutter. It is slimmer, lighter, and lined with jagged, razor-sharp serrations. This is a precision tool, used for rapid, slashing defense and for slicing to the soft tissues of scavenged fish or exposed invertebrates. Together, they represent a versatile, devastating weapon system capable of both blunt force trauma and surgical laceration. With its thick shell and its heavy weaponry, the lobster projects an aura of invulnerability. When a shadow passes overhead, perhaps the sleek silhouette of a reef shark or the heavy, muscular form of a large grouper, the lobster does not panic. It does not initiate a frantic, desperate sprint for the open water, because open water is the one place its armor can be bypassed by an attacker attacking from all sides simultaneously. Instead, the lobster reacts with a calculated, geometric retreat. Long, highly sensitive antennae sweep backward, feeling the contours of the rock behind it. The lobster's eyes, mounted on stalks, maintain a visual lock on the approaching threat. But its tactile sensors are doing the real work. It is looking for a very specific type of architecture. It is looking for a crevice. It finds a deep, narrow fissure in the limestone wall. With a powerful thrust of its legs and a sharp, downward tuck of its tail, the lobster propels itself backward, sliding smoothly into the dark recess of the rock. This is the bunker strategy, and against the vast majority of predators in the ocean, it is an absolute, impenetrable defense. The lobster wedges itself deep into the crevice. It positions its body so that its vulnerable underbelly is pressed flat against the unyielding stone floor. The heavy, armored carapace protects its back from above. The entrance to the hole is entirely blocked by the massive, raised claws, which are now braced against the walls of the rock, ready to snap shut on anything that attempts to cross the threshold. The geometry is perfect. The shark or the grouper circles the entrance, frustrated. They are built for the open water. Their heads are too large to fit into the narrow gap. They cannot flank the lobster because the limestone walls protect its sides. They cannot attack from behind because the crevice is a dead end. They cannot bite down on the heavy carapace because the angle is impossible. If they try to force their snouts into the hole, they are met with the excruciating, bone-crushing snap of the lobster's claws. The predator realizes that the energetic cost of extracting the lobster far outweighs the caloric reward of eating it. The math is broken. The predator turns away and swims back into blue, searching for an easier meal. Inside its bunker, the lobster remains perfectly still, its antennae twitching in the current. The armor has worked. The strategy has succeeded. The fortress remains unbreached. For millions of years, this dynamic is played out across the reefs of the world. The bunker strategy is so effective that it has allowed lobsters to thrive in some of the most predator-dense environments on the planet. But the ocean is an engine of continuous escalation. It does not allow any defense to remain perfect forever. The fundamental flaw of the bunker strategy is not a weakness in the armor, nor is it a failure of the claws. The flaw is the bunker itself. A crevice is a sanctuary, but it is also a dead end. It is a space with only one exit. By backing into the rock, the lobster has eliminated its ability to flee. It has voluntarily surrendered its mobility in exchange for structural protection. This is a brilliant trade-off when facing a predator that relies on speed and biting. But it is a fatal miscalculation when facing a predator that relies on leverage, patience, and the manipulation of confined space. The heavy armor of the lobster effectively filters out the casual hunters. It removes the sharks, the snappers, and the jacks from the equation. But by filtering out the generalists, the armor issues a direct invitation to the specialists. It summons the creatures that look at a heavily armored animal trapped in a narrow hole not as an obstacle, but as a guaranteed captive meal. The current shifts, bringing a new chemical signature to the entrance of the crevice. The lobster's antennae twitch violently. The incoming threat is not a fast-swimming fish. It is something entirely different. It is a predator without bones, without a rigid shape, and without any respect for the geometry of the rock. The octopus arrives like a shadow detached from the seafloor. It flows over the limestone, its body shifting color to match the mottled gray and brown of the rock, its 8 arms exploring the terrain with fluid, independent intelligence. The octopus does not rely on crushing jaws or explosive speed. It hunts through total, suffocating envelopment, and it views the hard shell of the lobster not as a deterrent, but as a convenient handle. The octopus detects the lobster wedged in the crevice. It does not hesitate. It does not hover outside the hole trying to find an angle. It simply pours itself into the gap. The lobster reacts with immediate aggression. Its massive claws snap out, attempting to catch the soft flesh of the invader. But striking an octopus in a confined space is like trying to punch water. The arms of the octopus absorb the blow, wrapping instantly around the heavy, calcified claws. Hundreds of highly muscular suckers adhere to the smooth surface of the lobster's exoskeleton, locking on with a vacuum seal that cannot be broken. This is where the environment turns against a defender. In the open water, the lobster might be able to use its powerful tail to violently flick backward, tearing itself free from the octopus's grasp. But the lobster is backed into a dead end. It cannot reverse. It is pinned against the back of its own sanctuary. The octopus uses the narrow walls of the crevice to its advantage. It braces its own body against the rock, creating immense mechanical leverage, and begins to pull. It does not try to drag the heavy lobster out of the hole. Instead, it uses its arms to pry the lobster's claws apart, forcing them wide, pinning them helplessly against the sides of the limestone fissure. The weapons are neutralized. The armor remains intact, but the armor is suddenly irrelevant. With the claws pinned and the lobster completely immobilized, the octopus brings its true weapon to bear. Hidden at the center of the radiating arms is a hard, parrot-like beak. It is the only rigid structure in the octopus's entire body. The octopus presses its beak against the lobster's carapace. It does not try to bite through the thickest part of the shell. It is far too intelligent for that. Instead, it probes for the weak points, the flexible, membranous joints where the heavy plates of the armor articulate, the spaces between the neck and the carapace, or the soft tissue beneath the eye stalks. The beak finds a seam. It bites down, slicing through the thin membrane, and injects a highly toxic, paralyzing salivary venom directly into the lobster's internal fluids. The effect is not instantaneous, but it is inevitable. The venom attacks the lobster's nervous system, disrupting the synaptic signals that control its powerful muscles. Inside the dark crevice, the desperate struggle begins to slow. The frantic snapping of the claws weakens to a sluggish twitch. The legs stop pushing against the rock. The lobster is fully enclosed in its impenetrable armor, perfectly safe from the teeth of the sharks, and it is dying. The octopus waits patiently for the venom to complete its work. Once the lobster is completely paralyzed, the octopus can consume it at its leisure, extracting the soft tissue from within the shell, leaving the heavy, calcified fortress completely hollowed out, perfectly intact and entirely empty. But the octopus is not the only specialist that has learned to exploit the bunker strategy. The reef is full of creatures that specialize in dismantling armor, and some of them use an approach that is far more violent than the quiet venom of the cephalopod. In another part of the reef, a different lobster backs into a hole, raising its claws to block the entrance against a passing grouper. The grouper moves on, and the lobster believes it is safe, but it has made a fatal error in its assessment of the terrain. The crevice it chose is not a dead end. It is part of a deeper, interlocking network of tunnels carved into the foundation of the coral. And deep within those tunnels, drawn by the scent of the frightened crustacean, something is moving. The attack does not come from the open water. It comes from the darkness behind the lobster. The moray eel is the ultimate master of the reef's internal architecture. Its serpentine body is designed to navigate the tightest, most jagged corridors of the limestone. When it detects a lobster wedged in the tunnel, it does not attack the heavy, defensive claws facing the ocean. It slithers through the dark, approaching the lobster from the rear. The lobster is built to defend its front. Its thickest armor and its heavy weapons are oriented toward the open water. Its rear flanks, particularly the segments of its tail and its walking legs, are less heavily fortified. The moray eel strikes from the shadows. Its primary jaws, lined with recurved, glass-like teeth, clamp down violently onto the base of the lobster's walking legs or the edge of its tail fan. The lobster panics. It tries to push itself forward, out of the hole, back into the open water to escape the ambush. But the moray eel does not let go. The eel throws its dense, muscular body into a violent backward contraction. It uses the jagged walls of the tunnel for leverage, bracing itself against the stone. The lobster is caught in a terrifying tug-of-war. Its heavy claws scrape uselessly against the rock in front of it as it is slowly, inexorably dragged backward into the suffocating darkness of the deep reef. The eel does not need to bite through the heavy carapace. It relies on the terrifying mechanics of extraction. Once a lobster is pulled deep into the tunnel, where the walls are so tight it cannot move its claws or flick its tail, the eel employs its pharyngeal jaws. This second set of teeth, located deep in the eel's throat, launches forward, biting down on the lobster's limbs and dragging them backward. The armor of the lobster is incredibly strong against compression, but it is highly vulnerable to torsion and tension. The eel twists and pulls. The joints of the lobster's armor groan under the extreme strain. Millimeter by millimeter, the eel dismembers the fortress. A leg is ripped free from its socket. A section of the tail is torn away. The lobster is dismantled, piece by piece, pulled apart at the seams. The thick, calcified plates that were meant to protect it from the ocean simply become rigid handles for the eel to grip as it shatters the animal from the inside out. These encounters highlight the fundamental paradox of armor in the natural world. A thick shell buys an animal time. It eliminates the vast majority of daily threats, allowing the creature to forage and reproduce in an environment that would otherwise consume it instantly. But armor does not grant immortality. It simply changes the rules of the game. It dictates that you will not be killed by the fast or the opportunistic. You will be killed by the patient, the specialized, and the intimately adapted. And even if a lobster manages to evade the octopus and outsmart the moray eel, it must inevitably confront a threat that it cannot fight, cannot hide from, and cannot armor itself against. Because the greatest danger to the lobster comes from its own biology. The thick, calcified exoskeleton is rigid. It does not grow as the lobster feeds and its internal biomass increases. The armor that protects it slowly becomes a suffocating prison. To continue living, the lobster must undergo one of the most stressful, dangerous, and terrifying physical transformations in the animal kingdom. It must molt. It retreats into the deepest, darkest crevice it can find. It stops eating. It begins to absorb the calcium from its own shell, weakening the structural integrity of its fortress. And then, in a moment of extreme vulnerability, the carapace splits open just behind the head. The lobster must violently extract its entire body. Its legs, its antennae, its heavy claws, even the internal lining of its gills and stomach, out of the old shell. It is a grueling, exhausting process. If it becomes stuck, it will die trapped inside its own former skin. When it finally pulls itself free, it is entirely unrecognizable. It is perfectly soft, completely pliable, and entirely defenseless. It is a creature made of jelly sitting in a world made of teeth. For several days, it must remain absolutely hidden in the dark, absorbing water to expand its new, larger body, waiting for the ocean's chemistry to harden a fresh layer of chitin into a new suit of armor. During this time, it cannot fight. It cannot use its claws, which are as soft as wet paper. If a predator finds it, it will be consumed in seconds. It relies entirely on the luck of isolation. It is a profound biological irony. To maintain the ultimate defense, the lobster must periodically strip itself completely naked, surrendering entirely to the mercy of a merciless environment. When the new shell finally hardens, the lobster emerges from the darkness. It is larger, stronger, and once again encased in a rigid, unyielding fortress. It raises its heavy claws. It sweeps its antennae. It steps out onto the abrasive rubble, dragging its weight across the ocean floor, daring the shadows to challenge it. It has survived the molting. It has survived the sharks. It has found a new bunker. But the reef is patient. The ocean does not rush its conclusions. Somewhere in the shifting currents, an octopus is mapping the geometry of the limestone, and an eel is slithering through the dark, waiting for a heavy shell to wedge itself into a corner. The armor holds until it doesn't. The bunker protects until it becomes a cage. The lobster survives not because it is invincible, but because it is durable enough to delay the inevitable. It walks across the fractured stone, a living fortress, carrying the heavy, inescapable knowledge that protection is an illusion. You can build the thickest walls in the ocean, but the reef will always find the seam. To survive as a small organism in the unforgiving architecture of the coral reef, you must commit to one of two absolute biological philosophies. You must either be fast enough to outrun the jaws of the world, or you must be completely invisible to them. The reef does not tolerate the slow, and it aggressively punishes the conspicuous. Every shadow holds a hunter, and every open channel is a killing field for the sleek, the muscular, and the hydrodynamic. Small fish exist in perpetual state of high alert anxiety. Their bodies tightly coiled springs ready to trigger a frantic, evasive burst of speed the moment a predator's silhouette breaks the ambient light. They wear muted colors. They hug the jagged limestone. They try to be nothing more than background noise. And then, suspended in the middle of this high-stakes arena, vibrating with completely unwarranted arrogance, is the clownfish. To observe a clownfish is to observe a creature that seems fundamentally disconnected from the terrifying reality of its environment. It is not camouflaged. It is painted in broad, high-contrast bands of electric orange and stark white, bordered in deep black, in the blue-green spectrum of the underwater world. It is a glowing beacon, actively advertising its exact coordinates to every predator within visual range. Furthermore, it is a notoriously poor swimmer. Its body is laterally compressed but relatively deep, and its fins are rounded and soft, shaped for delicate hovering maneuvers rather than the explosive thrust required to survive a chase. If a barracuda or a reef shark were to initiate a pursuit in open water, the clownfish would be consumed in a matter of seconds. It has no armor, no speed, and no ability to hide. Yet, when a massive grouper drifts too close to the clownfish's territory, the tiny, brightly colored animal does not flee in terror. It does not dart into a dark crevice to save its life. Instead, it turns its small, unarmored body to face a predator hundreds of times its size. It lowers its head, flares its rounded fins to make itself look as large as possible, and charges. It swims aggressively outward, snapping its tiny jaws, vibrating its body in a display of intense, frantic hostility. It behaves as though it is the apex predator of the ocean. The most astonishing part of this interaction is not the suicidal bravery of the clownfish. It is the reaction of the giant, the grouper, an animal capable of inhaling the clownfish with a single, effortless reflex, flinches. It hesitates, alters its trajectory, and slowly swims away, yielding the space to a creature it could swallow without chewing. The grouper does not retreat because it is afraid of the clownfish. It retreats because it recognizes that the clownfish is not standing alone. It is looking past a frantic orange fish, focusing entirely on the real estate directly behind it. The clownfish draws its absolute, unwavering confidence from the living fortress that anchors it to the reef, the sea anemone. From a distance, the anemone looks like a gentle, undulating garden of fleshy petals. It seems decorative, swaying softly with the pull of the tidal surge. But every predator on the reef possesses a deep, genetic understanding of what those soft tentacles actually represent. The anemone is a static, indiscriminate engine of death. Its entire surface is armed with millions of microscopic, pressurized harpoons called nematocysts, each one loaded with a paralyzing neurotoxin. To touch the anemone is to trigger an immediate, automated barrage of lethal chemistry. It is a minefield that fires at the speed of cellular reflex, dragging paralyzed victims into its central digestive cavity to be dissolved alive. This is the invisible wall that the clownfish hides behind. The clownfish is not brave. It is heavily backed. It projects an aura of extreme violence because it knows that if the predator decides to call its bluff and lunge, the clownfish only needs to dart back a few inches, burying itself in the deadly tentacles of its host. The predator's momentum would carry it directly into the anemone's firing line. The grouper calculates the trajectory, weighs the caloric value of the tiny fish against the absolute certainty of neurotoxic agony, and decides to find a meal that is not swimming in a minefield. But this brings up the fundamental biological paradox of the clownfish. How does a soft-bodied, unarmored fish survive, living inside a weapon system that is explicitly designed to kill fish? The answer is not a genetic immunity. A clownfish is not born invincible to the venom of the anemone. If a laboratory-raised clownfish, or one that has been separated from its host for an extended period, were suddenly dropped into the tentacles, it would be stung, paralyzed, and eaten just like any other prey. The immunity is not an inherent trait. It is an acquired disguise. It is a masterpiece of chemical espionage. The life of a clownfish begins as a microscopic larva, drifting helplessly in the open ocean currents. It is a period of extreme vulnerability, a terrifying lottery where 99% of its siblings will be consumed by filter feeders. For the few that survive and eventually settle down onto a reef, the absolute first priority, the only objective that matters, is finding a host anemone. A juvenile clownfish without an anemone is simply food waiting to be eaten. When the young fish finally locates the swaying tentacles of a host, it does not rush inside. To do so would be fatal. The anemone does not possess a brain to recognize the clownfish as a friend. It only possesses automated tripwires that fire when they detect the chemical signature of foreign biological tissue. The juvenile clownfish begins a tense, agonizingly slow ritual of acclimation. It approaches the perimeter of the anemone and hovers just millimeters away from the deadly fronds. Carefully, deliberately, it allows a single fin or the very tip of its tail to gently brush against the edge of a tentacle. The anemone fires. Microscopic harpoons deploy, injecting a tiny, localized dose of venom into clownfish. The young fish recoils, experiencing the pain and the physiological shock of the neurotoxin. But the contact was brief, and the dose was small enough to survive. The fish waits, recovers, and repeats the process. It brushes its side against the tentacles. It gets stung again. It pulls back. It does this over and over, sometimes for hours, sometimes for days. This process is not masochism. It is a calculated theft. The anemone's tentacles are constantly rubbing against one another in the ocean surge. To prevent the anemone from continuously stinging itself to death, its body is coated in a highly specific, proprietary mucus. This mucus contains a chemical signature that effectively tells the microscopic tripwires, "Do not fire, this is us." Every time the young clownfish touches the tentacles and retreats, it is deliberately agitating the host and smearing a microscopic layer of the anemone's own mucus onto its own skin. The fish is gradually covering itself in the host's biological password. As the ritual continues, the clownfish's own native mucus chemistry alters, blending with the stolen signature of the anemone. Slowly, the stings become less frequent. The triggers stop recognizing the fish as a foreign object. Finally, a threshold is crossed. The clownfish pushes its entire body deep into the dense thicket of tentacles, rubbing its face, its belly, its fins against the armed surface. Nothing fires. The trap remains completely dormant. To the mechanical, chemical sensors of the anemone, the clownfish no longer exists as a separate entity. It registers simply as another tentacle. The fish has successfully hacked the biological security system of the reef's most formidable stationary weapon. It has achieved total chemical invisibility. Once this infiltration is complete, the clownfish gains an impenetrable fortress. It can sleep, feed, and breathe within a space that means instant death to almost anything else. But the ocean does not operate on charity. Evolution is a strict accountant, and the anemone does not provide this sanctuary for free. The sea anemone is incredibly powerful, but it has a fatal flaw. It is entirely stationary. If a specialized predator, like a hawksbill sea turtle or certain species of heavily armored butterfly fish that have evolved resistance to the venom, decides to descend and begin grazing on the anemone's tentacles, the anemone cannot flee. It can only sit there and be slowly consumed. This is where the clownfish pays its rent. It becomes the mobile strike force for the stationary fortress. The aggressive, fearless charges of the clownfish are not just directed at predators trying to eat the fish itself. They are directed at anything that threatens the anemone. If a butterfly fish approaches to nip at the fleshy tentacles, the clownfish launches itself like an orange missile. It bites the intruder's fins, rams its body against the attacker's eyes, and harasses the larger animal with such relentless, vibrating fury that the grazer eventually abandons the effort and swims away. The clownfish is the enforcer. It protects the weapon that protects it. The symbiosis extends far beyond physical defense. The anemone is a living creature that requires oxygen and a clean environment to thrive. Deep within the dense cluster of tentacles, water circulation can become stagnant, allowing suffocating debris and harmful parasites to accumulate. The clownfish acts as a meticulous caretaker. It constantly wiggles and weaves through the base of the tentacles, its fluttering fins acting as a biological fan, driving fresh, oxygen-rich water deep into the host's tissues. It uses its small mouth to meticulously pick away dead tissue, drifting algae and parasitic crustaceans that attempt to burrow into the anemone's flesh. Furthermore, the anemone harbors microscopic, photosynthetic algae within its own tissues, which provide the host with essential sugars. These internal algae require nitrogen to survive and grow. In the nutrient-poor waters of a coral reef, nitrogen is incredibly scarce. But the clownfish, living its entire life within inches of the host, excretes its biological waste directly into the tentacles. The fish's urine and feces are highly concentrated sources of ammonia and nitrogen, acting as a direct, localized fertilizer for the anemone's internal gardens. It is a completely closed, perfectly optimized loop of survival. The anemone provides a heavy artillery and the impenetrable walls. The clownfish provides the early warning system, the perimeter defense, the housekeeping, and the agricultural fertilizer. They elevate each other from vulnerable, isolated organisms into one of the most successful and enduring micro-communities in the ocean. However, life inside the fortress is not a peaceful, egalitarian utopia. Space within a single anemone is strictly limited. It cannot support an infinite number of fish. Because of the spatial constraint, the clownfish have evolved a social hierarchy that is as brutal and unforgiving as the predators swimming outside. If you look closely at a host anemone, you will rarely see just one clownfish. You will typically see a small group, but they are not equals. The society is organized by strict, tyrannical domination, dictated entirely by size. At the very top of the hierarchy is the largest, most aggressive fish in the group. This fish is always the breeding female. She is the undisputed ruler of the anemone. Second in command is the largest male, who serves as her sole reproductive partner. Below this breeding pair is a small collection of progressively smaller, non-breeding subordinate males. The dominant female maintains her rule through constant physical intimidation. She routinely harasses, chases, and nips at the subordinate males, aggressively reminding them of their place at the bottom of the ladder. This violence serves a very specific physiological purpose. The stress induced by the female's constant bullying actually suppresses the growth hormones of the subordinate fish. She literally beats them into staying small. This ensures that they require fewer resources, take up less space within protective tentacles, and never grow large enough to challenge her or her chosen mate for dominance. The subordinates tolerate this abuse because the alternative is to be driven out of the anemone entirely, cast into the open ocean where their bright orange bodies will be instantly targeted and consumed. They accept a life of stunted, terrified subservience in exchange for the absolute security of the venomous walls. But the most bizarre and brilliant mechanism of this society is triggered only by death. If a predator manages to bypass the defenses and consumes a dominant female, or she dies of old age, the strict social structure is momentarily shattered. There is a sudden, massive power vacuum at the top of the hierarchy. The clownfish do not leave the anemone to find a new female. They do not need to. Clownfish are sequential hermaphrodites. They are all born with both male and female reproductive tissue, but they mature first as males. When the dominant female dies, the stress suppression on the largest breeding male vanishes. Without her constant harassment, a radical physiological transformation sweeps through his body. Within a matter of weeks, his internal chemistry completely rewrites itself. His male reproductive organs atrophy, and his dormant female organs activate and expand. The largest male fundamentally changes sex, transforming into the new dominant. breeding female. Once her transformation is complete, she turns her attention to the remaining subordinate males. The largest of the stunted subordinates, suddenly freed from the presence of the previous breeding male, experiences a rapid growth spurt and ascends to the position of the new breeding partner. The hierarchy ratchets up one slot. The social order is restored, and the new female immediately begins a cycle of violent intimidation against the remaining subordinates to maintain her newly acquired throne. This incredible biological plasticity ensures that the fortress is never left without a reproductive core. They never have to risk leaving the safety of the anemone to find a mate, because they carry the potential to become whatever society requires them to be. To look at a clownfish hovering among the swaying, colorful tentacles is to look at a masterclass in outsourced power. It is a creature that recognized its own physical limitations. It knew it could not outswim the barracuda. It knew it could not grow armor thick enough to stop the crushing teeth of the moray. So, it simply stopped playing by those rules. It found the most dangerous, indiscriminate killer on the reef, and through patience, pain, and chemical theft, it convinced that killer to become its bodyguard. The clownfish operates with the unbothered arrogance of a mafia enforcer, projecting absolute confidence because it knows the heavy artillery is always watching its back. It reminds us in the relentless, uncompromising mathematics of survival, brute strength is not the only path to dominance. Sometimes, the most powerful animals in the ecosystem are not the ones who possess the weapons. The most powerful animals are the ones who figure out how to hold the leash. The world is full of hidden mechanics, invisible wars, and stories buried just beneath the surface. If you want to continue exploring the unseen corners of our planet, subscribe to Earth's documentary, turn on the notifications, and step into the next chapter with us. The truth is always deeper than it seems. Nature doesn't leave a record of the weak, only the survivors. To uncover more of the most ruthless, brilliant, and ancient strategies on this planet, subscribe to Earth's documentary. Hit the bell icon so you never miss an expedition into the unknown. If you are fascinated by the brutal reality and the quiet beauty of the natural world, take a second to subscribe to Earth's documentary. Whether you are here to learn, to explore, or simply find an escape into the wild, your support allows these stories to continue. Join us, and let's journey deeper into the wild.